Hello, and welcome to this Apache Kafka Fundamentals. Kafka is a very interesting topic, and it plays a major role in many organizations. It is a robust platform that has grown over the past several years to solve many problems related to the transfer of data. In this course, we will explore what Kafka can do for you. The goal will be to provide a good understanding of key concepts and features of Kafka, while also providing you with some hands-on work. To get the most out of this course, you should have some programming experience. Kafka is flexible enough to work with many different environments and languages. Java is the most popular language to implement Kafka, but you will find it also can be implemented in other languages such as Python, Perl, C, and Ruby. Most of the focus of these hands-on code examples in the next lessons will be Java, but realize the choice to use Java is only because it's the most popular implementation. Because you may not be using Kafka in Java, I choose to avoid a lot of heavy coding examples in these lessons. The code that I do provide should be simple enough for you to apply or translate to another language of your choice. There's a lot to cover here, so let's get started. Welcome to Lesson 1, Kafka Concepts. In this lesson, you'll learn the essentials of what Kafka is. We'll start with a discussion of the birth of Kafka and see some of the key concepts of the Kafka solution. Then we'll compare Kafka to other potential solutions and point out the major advantages of using Kafka. Let's jump into lesson number 1. We're going to talk about Kafka concepts in this lesson. And we're going to start off by talking about how messaging works in Kafka. So to begin with, let's talk about the origin of big data, because big data has an important role in Kafka. Big data was introduced in 1986. Well, at least it was for me. In 1986 was the year that I first read a book by Isaac Asimov called Foundation. Later, he actually turned into a series of books. Foundation was a future-based novel. It had a galactic empire. It was actually quite massive with millions of worlds. In fact, you can actually see it says millions of worlds made up their society, and now the threat of 30,000 years of anarchy looms large. The protagonist was Dr. Harry Sheldon, and he had introduced this idea and theory called psychohistory. So to understand how this actually relates to big data, let's just see what psychohistory is all about. It's a fictional science, so it's not real, but it's designed to foresee the future events. It doesn't really work on individuals, so you can't really predict what someone's going to do next week or a year from now. But what it does do is allows you to have large bits of information that would be used by a lot of different people to determine what future events might take place. In fact, based upon this information that Dr. Harry Sheldon was able to gather from this galactic empire of over a quintillion people, he was able to predict that the empire itself was going to fall and there was going to be anarchy for the next 30,000 years. And so what he did is he took it upon himself to introduce into the future certain activities that would actually cause the galactic empire to rise in a quicker and more efficient manner overall. But again, we're talking about a quintillion number of people. That's a lot of people. That's 1 followed by 18 zeros. So this is what I referred to as real big data, not just big data. This is data of over a quintillion people. Now, when you're talking about big data, there are 4 challenge areas that you have to solve in order to be able to put together an entire software puzzle that handles big data really well. And one of those is the ability to collect data. Now, as far as the Dr. Harry Sheldon's environment, he didn't have to worry about this too much because the data was collected by the Galactic Empire on his behalf. In fact, it was actually mentioned several times in the book that there was no real rhyme or reason why they were collecting the data. They were just collecting the data because that's what they were supposed to do. But he was able to make use of that data. One of the challenges also you have to take care of in data is data transfer itself. So data transfer is, getting the data from point A to point B. Also, once it gets to point B, we have to be able to store the information somewhere. So that's going to be a big challenge as well. And then lastly, we need to analyze the data. And that's what Dr. Sheldon did. he actually took all the data and formed this theory about what would happen in the future and what kind of actions they could take place to modify what happened in the future as well. Now, as far as Kafka is concerned, it's not really designed to solve all four of these challenges. Normally, you'd use different software pieces for each one of these challenges, but Kafka focuses specifically on the data transfer element. So how we get the data from point A to point B, or actually from multiple point A's to multiple point B's, because you're not always going to get the data from one location, and you're not always going to send the data to one location either. Now, when it comes to data transfer, you also have some concerns that you want to take in consideration. One of those concerns is security. We want to make sure that the data not only gets from point A to point B properly, but we also want to make sure that it's not compromised. What I mean by compromised, that means no one steals the data or modifies the data to make it behave or look different. Another concern for data transfer is reliability. Not only want to make sure the data gets there, but all the data gets there. Normally it's going to be in small chunks, so we want to make sure all those chunks get there, and not only that, but they're actually getting there in the proper order as well. If you get 3 bits of data in different orders, then it may be difficult to figure out what the overall picture is. So we want to make sure it's reliable as far as the data transfer is concerned. Speed is also another big issue. If you're dealing with big data, it's a lot of information. We want to make sure it goes as rapidly as possible from point A to point B. Availability is important as well. We want to make sure that the data is going to be available in a timely manner. And then lastly, scalability is important too. What we mean by this is that you might have a small case scenario where you only really need one Kafka instance in order to be able to handle the data, but as time goes on, more and more data needs to be transferred, and that one instance is kind of difficult to do that. So we can scale out by including multiple instances, which we refer to as Kafka brokers. We'll see later in this video series. The last thing we'll talk about in this lesson is the difference between a traditional message queue and this thing called Distributed Streaming Platform, or DSP. In a traditional message queue, you have some type of software component, which we refer to maybe as a sender, and it's going to send that information, that message itself, to this receiver of some sort. And you see this quite a bit in lots of different software tools out there. You may have, like, say, for a program that will send information into, like, say, a database, for example. That would be a simple messaging queue. That's different from what we're going to see with Kafka. Kafka works a little bit different. We're going to have a sender, or possibly multiple senders, and it's going to send some kind of message, but there'll be not just one receiver, it'll be multiple receivers. That's why it's called a distributed streaming platform. It's not just going to go to just one single receiver. There's not going to be a single queue, essentially. In fact, to be a little bit more fair, instead of actually sending the information to the receivers, it's more like the receivers are going to request the data from the message itself. So the distributed streaming platform will allow us to have multiple receivers of information. We'll see a little bit later on, we don't really call them senders and receivers. You may call them other terms instead, like producers and consumers, for example, but the overall concept is similar to what you see on the screen right now. So now let's talk about the origin of Kafka. In order to be able to do that, we need to talk about LinkedIn and its story. So LinkedIn had a big problem they were facing. To begin with, they started with a single monolithic application they called Leo. And the purpose behind Leo was to serve up web pages, and it connected back-end databases, amongst others, a variety of tasks as well. Later on, they added another application called Cloud. Cloud was designed specifically for designing the member data, and also had to scale independently from Leo. In fact, both applications need to access the member profile database as well. Unfortunately, as time grew on, more and more traffic, as LinkedIn became more popular, really taxed Leo and the database access. So they decided to replace Leo with something that we refer to as an SOA, or a service-oriented architecture. Basically, individual services, they handle very specific tasks. They were all stateless, which allowed for a lot of scalability. And by 2010, they had 150 separate services, and by 2015, they had over 750 services. So this is a better solution than that big monolithic Leo beast they had. However, it did still have a problem as far as accessing data. So what they really needed to do is come up with a solution, and initially they came up with a customized solution where they had custom data pipelines. The pipelines were allowed for streaming and queuing of data. But unfortunately, they still didn't solve the problem overall. The problem with the streaming queuing data, if the client software or the services were not responding quickly enough, it caused a backlog, and that had caused a big issue as far as the data transfer is concerned. So what they really needed to have was some type of distributed messaging system. And they looked around and they found that none of the ones that are out there really solved the problem that they had. So they decided to go ahead and create one, something that would be referred to as kind of a universal pipeline. That was what Kafka was. And it had several goals initially. First goal was a single data transfer solution. So instead of having different types of solutions, there'll just be one solution. That's it. Everything went through Kafka. The second thing is, and this is kind of an interesting thing, is based upon the concepts of commit logs. Now, if you're used to databases, you might be familiar with commit logs, or maybe if you're used to working with file systems, you know about commit logs like journaling, for example. But the idea behind a commit log, let's just take a database example, for instance, is that any kind of action that takes place on the database, so if you were to write some information to the database successfully, for example, it creates a little log entry as far as what it was that was written. And the concept is if something goes wrong with the database, we can recover some of the data by using the commit logs and just basically replaying the commit log so it redid the actions that it did before. So that was the idea behind Kafka. It actually is a distributed messaging system, but it makes use of the commit log concept, because what happens is when messages are created and sent to something called the Kafka broker, that information is stored for a certain period of time, traditionally 7 days, but it can actually be configured to be a smaller amount of time or a larger amount of time as well. And that way, if the client software, which we refer to in Kafka as consumers, loses some of the data somehow, it can always go back and basically replay the log entries or reread the messages. So that's why it's based upon the commit log concept. Another goal was speed and scalability as well. Speed was important because there was a lot of data at LinkedIn that had to be transferred very rapidly and quickly. And if they had people who were on the website and the website was really slow in reacting, they would lose those people. And scalability was important as well because they knew they were going to have growth as time went on. So they had to make sure that the Kafka could grow along with their data transfer needs. Now, as far as Kafka at LinkedIn is today, there are over 500 billion events or messages that take place every day. Kafka is commonly used for things like real-time analytics, site monitoring, drive alerts, user activity information. So there are a lot of reasons why Kafka used at LinkedIn today. In this next lesson, we're going to talk about the Kafka Solution. And to begin with, let's go through a really brief history of Kafka. The first part we already know. We talked about the last lesson, how it was initially developed by LinkedIn. However, after LinkedIn worked on it for a while, they decided to open source the project in 2011. In fact, they handed it off to the Apache Software Foundation. And the first thing Apache Software Foundation did, like they do with most open source projects that are new, is they placed it inside the Apache incubator. It was in there for a short period of time as it was matured and released the full Apache project in October of 2012. Now, one of the interesting things that you may want to know about how Kafka works and how it's been adopted by many organizations is that the fact that it's written in Scala and Java. So Scala is a language you may not be really familiar with. It's not as popular as Java is, for example, but it stands for Scalable Language. It's interesting because it's like a scripting language. So if you've worked in Python or Ruby or Perl, you may be familiar with scripting languages. But it's a little bit different because it runs on top of Java Virtual Machine, and it has a lot of close integrations with Java itself. So for example, you can have Java and Scala classes, mixed together if you want to. Now, one important point that I want to make before I go any further in these lessons is that you can implement Kafka in many different languages. You can create Kafka code in Java, in Python, and Perl, and a bunch of other languages besides that. I don't want to make the language itself a big component of these training videos. So while I will show you some code as we go through these videos, it'll be mostly Java-based code since that is the predominant language used for Kafka. I'm not going to do a lot of coding in these video training sessions. I don't do that because I want to make sure that the language itself is not going to be a hindrance as far as learning Kafka. We're going to focus more on the concepts, and we'll just look at some code to back up the concepts that we learn throughout the class. So if you don't know Java or you don't know Scala, don't worry. The Java code that I'll show you is going to be fairly simple and straightforward, and I'll be able to walk through it and explain it to you. I'll even go through an example in a different language like Python, for example, so you can actually see how this could be used in different languages besides Java. So what exactly is Kafka? We already mentioned the fact that the whole goal of Kafka was to create a distributed streaming platform, so a DSP. The definition provided by the Apache Foundation is pretty telling, I think. It points out that Kafka allows you to publish and subscribe to streams of records. Now, the term publish and subscribe is something you'll see in other types of distributed streaming platforms out there. I'll talk about some of those in a future lesson. Although inside of Kafka, we don't normally use the term publish and subscribe. Instead of publish, we normally use the term produce. So we have producers that basically create streams of records or messages. And then instead of subscribe, we normally use the term consume. So we have consumers that are designed to basically receive the streams of records. So it's much like a message queue or enterprise messaging system, as they point out in the first definition point. Number two, it also allows you to store streams of data in a fault-tolerant way. This is a key component of Kafka that we're going to highlight throughout class. And again, I mentioned this in the previous lesson that by default, when a message gets received by the Kafka software, which we refer to as the broker, it stores it on the hard drive of the system for a period of time, traditionally 7 days, but you can actually make that a longer or shorter period of time. So it's a fault-tolerant way because if something happens and one of those subscribers or consumers can't get to that data for some reason in a timely manner, it'll still be there sometime in the future. So that way, if you have some downtime on your consumer software, it's not going to impact any type of messages that happen while the consumer software is down. And the third thing we'll talk about much later in the video series, but it's a kind of cool feature of Kafka, and that is it allows you to process streams of records as they occur. Now, what we mean by process is look at the data itself and possibly perform some manipulations on it. Maybe add some data, maybe transfer some data into something else. So we can actually process the data and do something with it. So Kafka has something called Kafka Streams that we'll talk about later in class or in these video series that will actually show you how that process works. And of course, it's designed to be scalable and fast. We talked about the fact that was one of the key important things that LinkedIn need to have to be scalable and as fast as possible. So what does Kafka actually provide? A really flexible scenario so you can handle many different types of data transfer situations. It has two primary functions. So it has the means to stream real-time data and that reliable fault-tolerant method. And also the ability to create applications that respond to the real-time data, including transferring the data using that stream operation I talked about before. So some key concepts. We're going to be using these terms throughout class. So we want to be familiar with the term cluster, which is a collection of Kafka servers. We're going to talk about this thing called a record or a message. That's the data that's being streamed. And when we do this, we're going to talk about the fact that there are several components of a record. The record is going to contain a key. We'll also contain a value, so there'll be key value pairs. And there'll also be a timestamp in the record itself. And then we need to know about these things called topics. Topics are ways of categorizing collections of records. They're the way that the consumers decide what data to read from a cluster. because you may have a collection of data that a consumer wants but another consumer doesn't want. So that's the point behind having a topic. And then we also are going to talk about something called a partition. So the purpose behind this is to handle that scalability factor, and that is that we want to make sure that we can actually have enough servers to handle all of the topic information, all the records coming into the Kafka cluster. And so instead of having the records go to just one specific Kafka instance, which we refer to as a broker, we can spread that across multiple brokers, and each one of those brokers is going to store this information inside of a partition. And what's important about the partition is, number one, it does allow for that scalability. It also allows for redundancy, we'll talk about too, so that you can actually have the situations so if one Kafka broker goes down, another one will have the information that will be available. And then also it provides this way that we can have an ordered, immutable sequence of records. So we know from the consumer point of view when we read from a partition that we're going to get the records in the order that they were received. And the idea behind immutable, by the way, is that once a record gets received, it cannot be removed from that partition. So if there's like invalid information that was inside that record, that can't be deleted from the partition. The producer of that record could create a new record later on, and that new record could have the updated appropriate information, but immutable means there's no way of going back and deleting old records. They're going to be there available for the consumer. We just have to have some kind of technique for the consumer to make use of updated new information that's accurate. Next thing we're going to do is talk about some of the advantages of Kafka. And we're going to start by doing something a little unusual, I think. We're going to talk about what other options are available to you first. Kafka is not the only solution out there, so you may want to consider some other solutions. I do want to give you a little forewarning here. I'll give you a list of these different solutions and some general ideas of what they are, what they consist of, but this is not going to be an in-depth discussion of the pros and cons of each solution. You want to explore each one on your own. It's kind of beyond the scope of this video series to go through every single advantage and disadvantage of each one of these solutions and compare them against Kafka. But I do want you to know what's available out there. So let's just talk about some of the options that are available. And we're going to start off by talking about something called AMQP, or the Advanced Message Queuing Protocol. So a few things you should know about this. This is an open standard. It works at the application layer of your software development. It has several features that are available to it. It has reliability, it is secure, and it's got some good interoperability as well. Next one we look at is widely used, that's called RabbitMQ. RabbitMQ is also an open standard. It's a little different than Kafka in this asynchronous, so that's something you may want to consider when you're trying to determine what type of distributed messaging system that you want to use. Some of the features it includes reliability, high availability, and multi-protocol support as well. The next one's really not exactly a direct competition to Kafka, but it does have some features that Kafka has, so I thought it'd include the Java Message Service. So the Java Message Service is a Java virtual machine embedded feature. It uses something called providers. So a provider is basically a software tool that lets you manage sessions, queues, topics, and similar types of things that you'll see inside of Kafka as well. Some of the features it includes is the ability to have message priorities. So this is having just basically a sequential series of messages. There's the ability to say this message has a higher priority than this message does. It does have some security features embedded into it. And there's actually two different models of the Java messaging service. It can have a point-to-point model, which is kind of like the traditional old message-to-client type environment, or we can actually have a model that's going to be a publish-subscribe model as well. And that's where it starts to compete a little bit against what Kafka can do. Another option we have available to you is Amazon Kinesis. Amazon Kinesis handles really high-volume data streams. It's really designed to work with Amazon Web Services and specifically three different components of it. one called Kafka Streams that's used to collect a whole bunch of different data and process the data in real time. Kinesis Firehose, which is really designed to have real-time streaming data to destinations that are Amazon Web Service based, like your Amazon S3 and Redshift. And then Kinesis Analytics. So this is actually designed not only to process the data, but also analyze it and make some type of determinate results based upon the information that it gathers. And lastly, we have Apache ActiveMQ. So ActiveMQ is written in Java. It has a fairly wide level of support. Its features include high availability, high performance, and it's actually very fast as well. So now you can see some of the options that are available to you, and I do recommend you go out and explore those options and see maybe if one of those might solve your solution better than Kafka would. Although I think you'll find Kafka actually has a lot of the features that those other ones have as well. It's quite robust. In fact, let's talk about some of Kafka's strengths. So one of the strengths of Kafka is its scalability. In fact, actually one of its strong points is that it's able to scale into very, very large data transfer situations. It's also very reliable too. One of the great things about the reliability is that you're pretty confident that the messages are going to get through to the consumers from the producers. Has high performance overall, and it's also very durable. Now, the idea behind that is that the data is stored at least semi-permanently in a file system structure. We'll talk more about how that works a little bit later on, in fact. But it's fairly durable in the sense that we don't have to worry about data loss, which is a really big issue for data transfer situations. It not only will store the information for more than just a brief period of time, but also we have the ability to have redundancy so that if one Kafka server/broker goes down, there'll be another Kafka server that can step in and will have all the data that the original one had to begin with. So you just take over all the functionality of the original Kafka broker as well. So that makes it more durable too. Hello and welcome to Lesson 2, Use Cases. It's helpful to see the basics of how Kafka is used in real-world scenarios. In this lesson, we'll do just that as we explore how Kafka is used in projects from Twitter, Netflix, and Yahoo. So now we're going to move on to Lesson 2 and talk about use cases. And the first thing we're going to do is just go through an overview of the use cases. So why present use cases in the first place? What's the point behind this? First thing we want to point out is that you'll see that major organizations use Kafka, and we want to see how some of those organizations actually make use of Kafka. We also want to provide some insight on how you might be able to use Kafka. If you start seeing some use cases, you may think of some ways that you can use it within your own organization. We also use this as a better way of understanding what Kafka can do. And I think this is a really important one too, is we want to demonstrate that Kafka can be implemented into existing projects. You'll see that a couple of the use cases that we'll go through, Kafka was not initially part of the solution, but it was added in after the fact when they found that it would be a better part of the solution to replace other parts that were already in existence. And then most importantly, you want to convince your boss. If you want your boss to come on board and start using Kafka in your organization, you may have to actually present some use cases to him to prove that it actually can be done. And the best way of doing that is to show you how some major organizations actually have used Kafka. One of the things I want to point out here, though, is that Kafka is not the entire solution. It never really probably is going to be the entire solution. Remember, when you're dealing with data, there's lots of components. There's the collection of the data, there's the storage of the data, there's the analyzing the data. Those are not things that Kafka necessarily does. Kafka is mostly the data transfer component of it. So most of the use cases that we're going to talk about are going to make use of other tools as well. And we'll point out what those tools are and talk about them in general. But the focus is really going to be on Kafka. It's not going to be on those other tools. We just want you to get an idea what those tools are being used for so you understand how Kafka fits into the overall solution that's being presented. I do suggest, though, that you want to learn about these additional tools. Each one of them could be a course all by themselves, but but they certainly are useful to know about because they might help you out in your overall solution as well. A few important notes before we get started here. First thing is, I'm not trying to cover all the details about the solution. We're just trying to get an idea of where Kafka fits in the big picture. Also, when I show you stats, they may not be up to date. We're not worried about that either. The stats are there just to prove to you that Kafka is being used in situations where a lot of data is being transferred. In fact, you'll see the stats might be from 2015, 2016. No doubt today those stats are much more impressive than they were back then. But I found the most recent up-to-date stats that were presented by these organizations, and those are the ones that I actually used. And also, we're not going to cover every situation where Kafka is being used within an organization. So, for example, when I talk about how Netflix uses Kafka, I'm not going to show you all the places that uses Kafka. We're just going to focus on one specific area. But just realize in almost all cases, if Kafka is being used for one specific use case in an organization, it's probably being used in other use cases as well. So that's something you want to keep in mind when you're exploring in more detail how this works. So which organizations did I choose to go through use cases on? The first thing I'll go through is show you how Twitter makes use of Kafka. Twitter is a good example. Netflix is another good example that has some good uses of Kafka. And then we'll also show you a demonstration how Yahoo uses Kafka as well. I do want to point out these are not the only organizations that are using Kafka out there. There are literally dozens and dozens that use Kafka. You can see that there's a link down at the bottom of the screen to give you a few moments to actually write that link down. But you can also find it on the Apache website if you search, or just search for Kafka use or clients that use Kafka or organizations that use Kafka, and I'm sure you'll come across that link. Now let me show you what that link actually looks like. So if you go there, you'll see what you see on my screen right now, although there might be some more companies there when you're all done. They call this the Powered By section. In fact, actually, it hasn't been modified in a while, so it looks like last time that it's been updated was 2016, so I'm sure there are a lot of other organizations that make use of Kafka. But the cool thing about this is if you want to know, for example, how Cisco uses Kafka, a lot of times the link will actually take you to more details about it. Now, in this case, it doesn't. It just takes you to Cisco's website. But you can also do some searching on the internet for, like, how does Cisco use Kafka, for example. And you may be able to find some articles that describe how Kafka is used at Cisco. But literally, there are dozens of organizations, and it includes large organizations and small organizations in here as well. So it's not just big organizations that make use of Kafka, but certainly some impressive organizations here. You've got IBM, for example. PayPal is listed in here. So a lot of other organizations besides the three that I'm going to show you that make use of Kafka. Okay, let's jump into our first use case. The first use case is going to be Twitter, or more specifically, a component of Twitter called Twitter Answers. It was launched in 2014 and is a free mobile measuring tool. Basically, it's designed to track application installs or app installs, and essentially the conversions of the installs. So when a user was asked to install an app, whether or not they installed it or not. Answers is part of a larger software tool set that Twitter provides called Fabric. It's a tool set that lets people create applications, lets them understand what the kind of user base they have, and other components to app-based programs. So let's talk about some stats to begin with. In February of 2015, so this was shortly after Answers came out, the developers wrote up a little article about this. And in that article, they had this quote. There are a few things that should pop out, I think, to you here. First of all, this is only 7 months after Answers was first released. And notice in the second sentence, they point out the fact that they get about 5 billion sessions per day. Now, remember, a session is not really a message. It's actually a collection of messages that occur. So it's not just one single message per se. In fact, you'll see the next sentence after that, they point out that hundreds of millions of devices send millions of events every second to the Answers endpoint. And so they've got to have some really reliable way of transferring that data, and that's going to be, as you'll see, Kafka. Also, they point out the fact that during the time that you read this message, if you read it in the normal speed, the backend will receive and process about 10 million analytic events. So this is actually kind of a cool thing, because what you're about to see is really the 4 different problems that big data has. Remember, that's collecting the data, transferring the data, storing the data, and analyzing the data. This is all done throughout this process right here. They're going to collect the data by using the devices themselves and sending that on to another service. They're going to transfer the data by using Kafka in a really reliable, stable fashion. And then they're going to store it in the back end. We'll see what tool they use for that as well. And then they have their own custom tool to analyze the data too. So this is actually the complete picture right here, an example how all 4 of those major concerns that people have with big data have been addressed in this particular product. Now, when they first started off here, they had some challenge. The data had to be reliable. This was key because if something went wrong, the device couldn't communicate and present the information, we had to allow them to retry the delivery again. So that was actually one of the challenges they had to face when they put together this particular software platform. It had to be real time, so something had to trigger a delivery from the producer side. And of course, the data had to be actionable as well, which means some kind of action had to take place based upon the data that gets analyzed. So let's look at the producer solution. Now remember, in a publish-subscribe environment, you've got a producer. The producer actually creates the data, and then you also have a consumer. So in some cases, the producer could be simply a Java-based application that sends data to Kafka, but you're going to see that for Twitter Answers, the solution is a little bit more complex. So the first thing that happens is obviously the device is going to create some type of data, some kind of record or message that we want to eventually send to Kafka. And that initially gets sent to an Amazon ELB. ELB stands for Elastic Load Balancer. This is simply a way to spread out the load so that the data doesn't actually go all to one single location. They use a Golang app instead of a Java program. They use a Golang app instead to then send that information to Kafka. Now, a couple of things that are important about this. Once the information gets to Kafka, it's possible that the consumer solution doesn't read that information right away. So one of the reasons why they chose Kafka here is it does have a stable location where it stores information. I've mentioned in previous lessons that typically Kafka will store messages or records for a period of 7 days by default. However, there are going to be a lot of records for Twitter Answers, and they realized early on they weren't going to be able to store 7 days worth of messages. So they configured Kafka so it only store the information for a few hours. But still, that provides the advantage that if there's any kind of problem on the consumer side, that the consumers can't read the data for some reason because they're down or there's a network disconnect or something happened, the data will still be there within a reasonable period of time so that consumers can read the information later on. So that's the producer solution. And then the consumer solution, remember, consumer is what's going to retrieve the information and do something with it. Obviously, that's going to start off with Kafka. So the consumer application is going to read some data from Kafka, and they make use of something called Amazon Storm. Another great project, if you get a chance to take a look at it. It does real-time data processing. They could have actually used Kafka Streams here if they wanted to. That was another option that we'll talk about later on how that works. But I'm sure Amazon Storm, since they're doing a lot of things within Amazon, probably was a good solution for them here. And especially since they're eventually storing this all on Amazon S3 backend. So there's a good example how Twitter Answers shows you a complete solution of using Kafka as the data transfer tool. Now let's talk about use case number 2. Use case number 2 is Netflix Keystone Data Pipeline. So you're all familiar with Netflix, the video streaming processing service. The Keystone Data Pipeline does not handle the video streaming, but it handles data that's associated with that, plus some other data we'll see as well. One of the things that's really nice about this particular use case is it's a great example of a solution that did not initially use Kafka, but later as time progressed, they saw the need for Kafka Solution because of some of the features that Kafka provides. So the pipeline itself handles lots of different things. One thing it handles is viewing activities. So like, for example, if you're watching a movie and you decide to pause it 10 minutes into the movie, if you log out and log back in again and go back to that same movie, it remembers that you were actually 10 minutes into that movie. So activities like that are going to go through this data pipeline. Also, any type of other user interface activities, like if someone clicks on a movie but they decide not to actually watch it, that would be part of the data pipeline as well. Other information that's in the data pipeline will be error logs, performance-based events, troubleshooting events, and diagnostic events as well. So to give you an idea how much this is used as far as Kafka is concerned, let's look at some of the statistics. In 2015, which is the last year I could find statistics for how Kafka is used at Netflix, they were saying that they had about 5 billion events per day and about 1.3 petabytes of data per day. So that's a pretty impressive amount of information that's being transferred through Kafka. And include that is some peak loads of about 8 million events per second and about 24 gigabytes per second as well. So it can handle a lot of information and a lot of records really quickly too. The first version of this solution did not include Kafka. It made use of something called Chukwa, in which the producers, which would be the different applications and features and services, would send information to Apache Chukwa. Apache Chukwa is an open source project. It's really designed to work in relationship to the Hadoop distributed file system. So it has a lot of the features that Hadoop provides as well, scalability, robustness, and things like that. The Apache Chukwa would send the information to the Amazon S3 service, and then it would send it eventually on to Hadoop. This was a good solution initially, but there are a couple drawbacks. Because of the way the events are collected and written to the Amazon S3, there is a latency from end to endpoint. So from the moment the producers create the messages to the point in which Hadoop actually gets the messages and does something with them, there's a latency of about 10 minutes overall. At the point where they first created this, that wasn't a big deal. They were only doing batch reports every hour or daily, so it wasn't really a major problem at the time. But as time progressed and Kafka became more and more popular, they realized that it would be nice to have some real-time analytics take place. So in version 1.5, they added a branch. So they took some of the messages that were going through Apache Chukwa and they branched them off into Kafka. About 30% of the messages were branched off into Kafka. So by branching them off to Kafka, they were able to have Apache Chukwa be a producer, essentially, that was sending on certain messages to Kafka. And then it went to a router, and the router actually would tee the information off to two things, Amazon's Elastic Load Balancer, and also another set of Kafka servers as well, which would actually further transform the data, manipulate the data, and do some information with it as well. And then there were some consumers that were reading either from the initial Kafka data stream or from the revised Kafka data stream as well. As a result, they ended up with about 150 clusters overall, so 150 collections of Kafka servers, about 3,500 instances overall, and again about 1.3 petabytes of data that were happening per day. As time went on, they realized a higher percent of those messages that were going from the Apache Chukwa to Kafka, it went above 30%. It started becoming more relevant to have all the messages be real time. So version 2.0, they decided to take out Chukwa altogether and implement just a single Kafka cluster for all the messages to go to. And that sent the information on to the router. They didn't actually get rid of that. They still have that router to break up the data into different components and places. Some of the information went on to the Elastic Load Balancer. Some went on to the Amazon S3 and Hadoop. And then some went on to the Kafka system where the consumers would read the data from there. One of the reasons why they did this is because, again, they found more and more often they needed to have some type of way of getting the data real time and not wait 10 or 15 or 20 minutes after the event was created to actually do something with the event. And secondly, they found that having the other solution was a lot more complicated by having Kafka as the front end distributed messaging system, it made it a lot more simple actually to deal with the data overall. Okay, let's get into use case number 3. Use case number 3, we're going to talk about Yahoo. And unlike the other use cases where I went into very specific projects, I'm going to talk about Yahoo in general terms. There are several organizations that use Kafka at Yahoo. I'm just going to talk about a couple of them in general. And then I'm going to talk about a project that Yahoo has developed that you might be interested in learning more about. So to begin with, again, many teams within Yahoo use Kafka. So for example, there's a media analytics team. They use Kafka for real-time analytics pipeline. And there's also something called the Data Highway Rainbow, which is a service that Yahoo will host. And the idea behind it is it offers the ability to do collection of data or events, transportation of data, and also the aggregate of data, and it's all based on a service that they've created overall. So at this point in time, if you were to look at statistics that Yahoo provides back in September 2015, you can see they handle over 20 gigabytes of compressed data at peak bandwidth using just Kafka alone. The Kafka clusters handle all that data. Now again, there's a lot of ways that Yahoo makes use of Kafka, but what I wanted to point out was that since it's become such a prevalent thing at Yahoo, they've invented something new that's kind of interesting called the Kafka Manager. So this is an open source web-based administration tool that you might be interested in learning more about. I'll point out where you can get more information about it. It's not really going to be a part of this video training session, but I wanted to mention this to you because you might find it to be a useful tool. And it also shows you that Kafka is not just being used by organizations, but the organizations are actually building tools around Kafka that might be open source and made available to you as well. So the features of this open source web-based administration tool include the ability to manage multiple clusters using the web-based tool, replication management, so you can handle the replication of data between the different partitions, and also topic creation. All those things we can actually do on the command line, and we'll demonstrate those as we go through this video training series, but the web-based tool might make it a little bit easier to deal with. It also shows you a visual description of the cluster, so you can see all the components of the cluster, all the different Kafka brokers that are part of the cluster, for example. Now, if you want to learn more about this project, I recommend going to this site right here. So going to github.com/yahoo/Kafka-manager. And just to give you a brief glimpse of what that looks like, I'll go to that myself. So here's that GitHub site. What you probably want to do when you first go here is look at the README file. So there's a readme.md file. And it gives you a good idea of what this tool actually does. It actually does a lot more than I just mentioned. I pointed out some of the highlights behind it, but there's some of the stuff that we hadn't really even talked about yet. So I just point out what we understood from what we've gone through so far in the video training series. So they give you like a little example, by the way. There's some clusters here and some operations we can perform on it. We can modify the clusters, disable the clusters, and so forth. So it's a good tool. I think you should recommend looking at it. See if it might be useful in your environment as well. Hello and welcome to Lesson 3, Kafka Design. Before you start working with Kafka, you really should understand the design principles of Kafka. In this lesson, we'll start by describing key features and concepts, including Kafka APIs, topics, logs, producers, and consumers. We will also discuss the different ways that Kafka can be used, including as a message system, a storage system, and for stream processing. In this next lesson, we're going to talk about Kafka design. So lesson 3 is going to focus on really kind of how Kafka is designed and really some key important terms that you should realize and some concepts too. I think this is a really important lesson because one of the biggest challenges I've noticed in learning Kafka for most people is just really getting their head around how the whole process works. So we want to get an idea of what the design features of Kafka are, the different components, like get a better idea of what a producer is, what a broker is, what a cluster is, what topics are, what partitions are. All those things we're going to talk about in this lesson right here, and give you some real hands-on examples on how that process works. The first thing we're going to get into, lesson 3.1, is going to be distributed streaming platforms and describing what they are and how they might be better than the old school traditional single thread platforms that you may be used to in the past. Now, before we do that, let's go back through and talk about the definition again of Kafka that's provided by Apache. So remember, Kafka lets you publish and subscribe streams of records. It also lets you store streams of records in a fault-tolerant way and allows you to process streams of records as they occur. Now, the reason why I brought this up again is because item number 1 and 2 are going to be a key component to understanding how Kafka works in lesson 3. So we're going to talk about a lot about this publish-subscribe of records and events or messages, and we're also going to talk a lot about in lesson 3 how this information is stored in a fault-tolerant way. We're going to revisit that again in lesson 5 when we talk about installing Kafka and get a little bit more into the fact that it stores its records or messages on the hard drive and some pros and cons behind that. But those first two things right here, you really want to think about as we go through lesson 3, because you're going to see those different definitions hammered home several times throughout what we're going to talk about. I won't go too much into the third item, it lets you process streams of records as they occur, until later on in this video training course, but it certainly is a key component of what Kafka can do. So before we get into a distributed streaming model, let's talk about the old school non-distributed streaming model. So we can kind of see where we came from and get an idea why Kafka might be a better solution overall. So this might be going really old school for you. I don't know if anyone out there remembers when we had just the server. So if you remember this was back in the days where you had one single solitary server that it was your web server, your mail server, your file server, all that kind of stuff was that one server. And then the client programs would actually connect to that to do whatever they need to on that server, like retrieve email or look up something on your website or whatever. The problem with this right here, obviously, is you have a single point of failure. That server could go down, which means everything in the entire organization goes down. And of course, the load that's on that one server could be pretty tremendous as well. So as time went on, we went to a situation where we had multiple servers. So we had like a database server, an authentication server, and then clients would actually contact those servers as necessary. So now we've distributed the load so that the one server is not handling all of the stuff, but still clients have to connect to these individual servers, know where those servers are, know what kind of data retrieve from them, how to retrieve the data, and so forth. And as time went on, things got more complicated. You'd have, say, multiple servers and multiple clients all trying to connect to those servers. It got to be a real big headache overall. Not to mention the fact that it could even be a little bit more complicated than just this. In a environment of nowadays, there's not really such a thing as necessarily as the server, and even a server could be a client itself. So, for example, you could have these servers that have clients, but there could be a machine that acts both as a client and a server. So maybe some kind of back-end server that client utilities or software would talk to, but it might talk to maybe a database server, so it might be a client of the database server. So it can be really complicated. In fact, I think what you see on the screen right now is not nearly as complex as most traditional environments are. I would probably need to have dozens of different red boxes with servers and, of course, hundreds if not thousands of client systems as well. And the diagram will be a lot more difficult to follow overall. This is different than how we handle things in a distributed system. So in a distributed system, we are going to have all these different servers just like we did before. But those clients aren't going to connect directly to those servers. Instead, what they'll do is they'll talk to a Kafka broker. So the messages will be sent from the database server, the authentication server, the web server, the backend server to either a single Kafka broker, or in order to provide the ability to actually have redundancy and scalability, maybe multiple Kafka brokers. I just put one Kafka broker in this example just to make it a little simple overall, but we'll see how we can have multiple Kafka brokers in later examples. The messages go to that Kafka broker, and then the client utilities will ask for the information from the Kafka broker as necessary. So as you can see, the level of complexity is not nearly as it was before. And yes, you could actually have a system that actually works as both a producer of records to the Kafka broker and a consumer of records to the Kafka broker as well. I didn't put that in this diagram, but certainly we could do that as well. Now you might think to yourself, well, didn't we go back to the situation where we've got a single point of failure? And the answer is none of you actually put together the Kafka cluster properly. There's ways to actually distribute the load across multiple systems, and there's ways with Kafka to have redundancy so that if one of the Kafka brokers were to go down, it wouldn't lose all of its messages. There'll be another Kafka broker that can take up and continue to take care of those messages that are coming from those different server utility software programs. So as far as the Kafka broker is concerned, a Kafka broker is going to be just basically a single Kafka server. And I'll show you, by the way, later on in the course how to start up a Kafka broker very easily. It's a very easy tool to go ahead and do that. It's used to actually collect the data that's being sent for the producers, and it'll store the data for a specific period of time. I've mentioned previously that normally it's 7 days, but that's something that can be configured for the Kafka server itself. It will also send the data to the clients, or what we call consumers, as requested. A collection of Kafka brokers working together is referred to as a cluster. We have a publish-subscribe environment, so the producer is the published part of the Kafka environment. It's the one that creates the data and sends that to the Kafka broker to store the information. The data is referred to normally as a record or a message. I kind of use the term interchangeably because a lot of different documentations and tutorials use both either message or record, so you hear me use both terms throughout the entire video training session. It's referred to as the publisher also because it publishes data or creates the data and makes it available to the broker. And it's Kafka broker that's designed to handle the data once it receives it. So after the producer passes it off, it doesn't worry necessarily about storing the information anymore. I guess if it was like a database server, it might store the information, but other servers may not do that. It just may create a record, send that record off to the Kafka, and just forget about that information entirely. But Kafka is going to handle the data from this point as far as how to provide it to other software utilities out there, and those other software utilities are going to be the consumers. So the consumer is going to basically read the data from the Kafka broker, or more specifically request the Kafka broker to send the data to it. It's referred to as subscribing because when a consumer starts up, it will ask the broker to see a collection of messages. So the collection of messages are something referred to as topics. We'll discuss those a little bit more in detail in the next few lessons. But consumers going to say, hey, I want to see all the messages for this particular topic or this collection, and then the broker will provide the messages for that particular topic. With that said, by the way, that also means that producers will write messages not just to Kafka broker in general, but to a specific topic so that the consumer can read from that topic and get the information really easily. Okay, in this next section, we'll go through an overview of the Kafka APIs. So first of all, let's talk about what an API is to begin with. You may not be familiar with the term, but an API stands for Application Programming Interface. It really provides an easy method for two applications that may not have a common ground to talk to one another. So these two applications may not be the same language, may not speak the same terminology, but by using an API, it makes it really easy to communicate between the two. And typically an API will include things like the protocols it uses for the interface itself, some routines or procedures that are going to be performed, and some tools as well. Now, as far as the Kafka API is concerned, the first thing you should realize it is a TCP-based protocol. It uses a binary protocol that runs on top of TCP. It's backwards compatible. It uses a request-response messaging pair. There's no handshake that happens during the communication. And probably the most important thing here is that the requests are guaranteed to be processed in the order they're received. So when a producer sends messages to a broker, the order the producer sends the messages is the order the broker will retrieve the messages and store them. Some additional details are important to know about the protocol. First of all, it is a high-grade performance communication. The communication is language agnostic, although you'll find that most people do use Java because there's a Java client provided. But I will point out in lesson 4, when I go through some details of the APIs, that there are plenty of other clients out there besides Java. So if you decide that you want to use Kafka in Python or Perl, or basically a couple dozen languages that support Kafka, you can use those instead. All right, as far as the APIs are concerned that provided in Kafka, we have the producer API that is going to be used to produce the messages that are being sent to the Kafka broker, and the consumer API, which will be used to retrieve the information for the Kafka broker. And those make sense because we've already talked about producer and consumers so far. We also have something called the connector API, which I won't talk about too much until towards the end of the lessons. So lesson 10 will talk about the connector API and the function that it performs. But in a nutshell, the idea behind the connector API, or just Kafka Connect it's called, is the ability to take data that's not coming from a traditional producer and make it be part of the data set that's being sent to a broker. So it allows you basically to scarf up a bunch of data coming from, like, say, I don't know, maybe a backend database, for example, and put it into the Kafka broker very quickly and easily. And then there's one more that we'll see later in class. In lesson number 11, we'll talk about the API for streams, or just Kafka Streams. The API for Kafka Stream is going to be able to allow us to do manipulation of the data in a real-time environment. It's actually kind of cool because it doesn't really run as a standalone service. It can be running as a part of an application that you've already built that can actually read the data that comes from the Kafka broker and manipulate the data, maybe add some more information in it, maybe do some aggregates so it actually pulls data from other sources, or even transforms the data to a different looking data structure overall. So the next thing we're going to talk about are two really important topics. One's called topics, the other one's called partitions. So we've talked about producers and consumers, but let's be really clear about what a producer and consumer is. So a producer is going to create and send data to Kafka brokers, and consumers are going to retrieve data from Kafka brokers. But the real big question here is exactly what data does a consumer retrieve? I mean, you could have a situation where you've got a lot of information that's on the Kafka broker, but only some of the information you want to retrieve if you're going to be building the Kafka consumer. And the answer to this question is this thing called topics. Basically, a topic is like a category of messages. Producers will send messages to a specific topic, and consumers will retrieve messages from that specific topic. And that topic is something that you can create within Kafka itself. I'll give you a demonstration how to create topics, in fact, later on in lesson number 5. To give you an idea what we're talking about, let's look at a visual example of what a topic looks like. So we have these producers who are sending information to our Kafka broker, and of course our client is retrieving information from the broker as well. But again, the clients don't retrieve all the information. The clients will actually subscribe to a specific topic that they want to retrieve the information from. And so that topic is going to be stored into the Kafka broker system. By the way, if you look at this diagram, you'll see that the icon that appears looks very much like a symbol that you might see that represents a hard drive, and that's because data is stored on the hard drive for Kafka brokers. Now, I know a lot of people, when they first see this, they think to themselves, wait, this is supposed to be something that's really supposed to be fast. How is it going to be fast if we're using a clunky old hard drive to store this information? I will discuss in lesson number 5, when I talk about setting up a Kafka broker, how the hard drive actually can be faster than storing information in RAM. And at the very least, if you're using a hard drive space, you have a lot more space available to you. One of the problems with Kafka sometimes is that you face a large amount of data. You don't want to try to store all that information in some type of RAM or flash drive situation. So I will discuss that later on. I know it's something that when people first see this slide, they kind of hesitate because they're thinking, I don't know about storing this information on the hard drive. I need it really quick. But we'll talk about how to deal with that later on and how that works. But for now, we're going to focus on the topics. So maybe I've got two topics, a topic A and a topic B. You can name the topics whatever you want. I just chose A and B to make it a little easier in this example. And so what happens when a producer will create a record to send to the Kafka broker, it says, hey, I want to send that to topic A, for example. So another client utility can actually say, I want to retrieve that information from topic A. And then another producer can send a message also to the broker and say, this is for topic A as well. And of course, the client would retrieve that information too. So you could have multiple producers, multiple software pieces sending information to the same topic, and then a client could be just pulling the information from that particular topic. And of course, later on, another client could actually pull that same information from that same topic. Now, the only drawback about this that you might think about is, well, if I've got this one Kafka broker, and that one Kafka broker has one single hard drive, and I'm sending all the information for all my topics there, that's going to cause a little bit of a problem, because now we have this situation where we've got a single point of failure. And that's where the idea of partitions come in. So that with partitions, if you only have one single Kafka broker, then partitions don't come into play whatsoever. But the idea behind partitions is if you have multiple brokers, the data for a topic is not just sent to one single broker, but can be sent across multiple brokers and also replicated across several brokers as well. Each instance's data is called a partition, and again, the partitions can be replicated so that we can have redundancy in case one of the partitions goes down, one of the Kafka brokers becomes unresponsive. We can solve that pretty easily by having a duplicate or a replica of that partition on another Kafka broker. And because of that, you'll find that consumers can read messages from any partition, not the same partition each time. In fact, consumers are pretty smart. If they find that one partition is no longer available, it'll tell the Kafka broker about that, and another partition will be made available as long as they have that redundancy set up. And we'll demonstrate how to set that up later on as well. Also, each consumer keeps track of what messages is read by a numeric value represented by something called an offset. We'll just briefly mention the offset now because it kind of comes into play in this example, but we'll talk more about it in a later lesson. So if you like visual examples, maybe this helps it out a little bit here. Let's say we've got some Kafka brokers. Each one of those Kafka brokers is storing information for topic A. So imagine northbound above this, it's not in the diagram, but they've got some Kafka producers that are sending information to the Kafka broker, and that information is being passed into these different partitions. The way it goes about doing that we'll describe later on. It could be like round robin. So a message will come into the Kafka broker. It'll be sent to one broker, then it'll send to the other broker. We'll talk about how that works later on. We have to introduce something called Zookeeper before we can understand how that round robin process works. But you can also do some load balancing too. So you can have one Kafka broker get more messages than another Kafka broker as well. But in this case, we use a round robin approach. So those messages that are going into the Kafka brokers are spread across these two different partitions. One thing that's kind of hard to see in the diagram that I want to highlight though is this is not replication in this example right here. This is a total of 8 different messages or 8 different records. They get a numeric value of 1, 2, 3, 4 in each of the Kafka broker partitions, but that's a total of 8 different separate messages. There's not duplication going on in this case right here or redundancy. So what that means is when the consumer reads information from there, we can have one consumer read from one partition, for example, and maybe another consumer read from another partition. Or we can have one consumer read all the partitions and retrieve all the information. Depends on how we set up the consumers. We'll discuss something called consumer groups later on in this course, where you actually learn how you can spread the load out on the consumer side, just like we can spread the load out on the broker side as well. In this next section, we'll provide some more details about producers and consumers. Producers are the ones that create the new messages. They send them to the Kafka broker, and the messages are sent to a specific topic. You can also send the message to a specific partition, but typically that's not done that way. Normally the broker decides what partition the message is going to go to. Typically you're going to use the producer API to create the producer messages. And also sometimes producers are called publishers or writers. Consumers are the ones that read the messages from the Kafka broker. They can read from one or more topics. Also, the consumers are tasked with keeping track of basically where they are in the topic by using something called an offset. An offset is a numeric value assigned to each message. So a consumer can keep track of where it is inside of the topic. So when it reads from the topic, it knows where to start reading from. This allows consumers to catch up if there's any kind of downtime. And keep in mind that consumers could lose access to data if there's a very long downtime, because the messages have a time to live on the Kafka broker. That's a configurable option, but at some point in time, the messages will be removed from the Kafka broker. Now, one topic we haven't talked too much about yet is consumer groups. The idea behind this is you might have a situation where a consumer has to read a massive amount of information, and it's just too much for that one consumer to handle. So multiple consumers can read from a topic. They can share the load between one another. So each consumer is going to read messages from one or more partitions. Because of that, you need to think about, when you put together your partitioning scheme, how many consumers you'll have in your consumer groups. For instance, if you're going to have 3 consumers, then it might make sense to have 3 partitions. What wouldn't make any sense is to have more consumers in a consumer group than you have partitions. So for instance, if you have 5 consumers in a consumer group, it wouldn't make any sense to have just 3 partitions, because each of those consumers is going to read from one or more partitions, but they won't be reading from the same partition. So 2 consumers in a group can't read from that same partition. They each have to have their own partition or one or more partitions they're going to read from. So if you have 5 consumers trying to read from 3 partitions, that really means 2 consumers are really not going to do anything at all. They're just going to sit there idle, doing nothing whatsoever. When the consumers first try to connect and start reading from the partitions, they'll be assigned a partition at that point in time. From that point on, they'll just read from that partition whatever happens to be placed in that partition. Now, it'll be up to you, when all is said and done, to take all the information from those different partitions and merge them back together again into one single data set. That's going to be entirely up to you as far as how you're going to actually do that on the end where you're reading all the data from in your consumer. So this next topic, we're going to talk about how Kafka can be used as a messaging system. As you'll find out, Kafka can have several roles within your big data system. In this case, we're just going to focus on Kafka just as a messaging system. And to begin with, we're going to talk about, just in general, enterprise messaging systems. So they're designed to allow transfer data between 2 systems, and there are 2 different types you can utilize. One type called queuing, which is not what Kafka typically does, and then the publish-subscribe method that Kafka utilizes. Regardless of what type you're actually using, there are some considerations you have to keep in mind when you're picking the type of messaging system that you're going to use. One's going to be security, so we have to make sure the data is going to be secure. We also have to consider data routing, so how is the data going to get from point A to point B? The reliability of data is going to be a key important point. Data persistence, how long the data is going to be available for the consumer to pick the data up. Redundancy, which Kafka also handles. And load balancing, so we can share the load across multiple Kafka brokers. Some messaging system features that Kafka provides. One that's really important is a strict order messages. So you know when you're reading things from the consumer, you're getting the messages in the same order they were created from the producer sides. We also have a configurable message time to live. When you specify that you want to create a topic, you can say how long the messages on that topic are going to exist. These can be stored on the hard drive, as we'll mention in a few minutes here, but also it's something that is configured by topic basis, not a partition by partition basis or by producer or by the Kafka broker, but each topic has a separate time to live. Consumer groups allow for more efficient message collection because you can spread the load of retrieving the messages across multiple applications. And partitions provide us that load balancing feature that we need in order to make it easier for us to have the Kafka broker store all the information in a timely manner. So this next section, we're going to talk about Kafka as a storage system. When queuing systems are used, they don't typically store messages after they're read. The message goes from the publisher into the queue, and then once it gets read from the subscriber, then the message is gone. Unless, of course, the subscriber decides to keep it permanently on that end of the process. With Kafka brokers that can store messages for a configurable amount of time, typically 7 days, but that's something that can be changed. And the data is stored persistently on the hard disk. Data can be replicated for fault tolerance, which means we can have multiple partitions, and the partitions can actually have backup copies, essentially, of the data. One of the keys to fault tolerance is the fact that if you have one partition that's storing the information that's coming from the producer, and we have, like, say, 2 backup copies, 2 replications, essentially, the message is not considered to be written until it is persistent on all storage devices. So it'll be written to the broker that has the partition for the data itself, and then the 2 replicas, and once all 3 of them confirm the data has been stored, then it's considered to be written. Otherwise, if it's not considered to be stored and written, then a message goes sent back to the producer saying that that data has not been written, and the producer can resend the information if necessary. So performance is not really impacted on persistent data on the server. This scales really well. One of the things that kind of bothers people a little bit about Kafka is that it does use physical storage devices, and so you might consider this to have an impact on performance. It doesn't if you configure it properly. We'll talk a little bit more later in the lessons how you can make it so that the data is actually fairly quickly easy to read and write. And we'll talk about some of the hardware considerations that you need to take into place when you actually create the physical storage devices that the Kafka is going to store the information on. The next thing we're going to discuss is how we can use Kafka for a stream processing service. So first of all, let's kind of talk about what stream processing is all about. It is a really important component to big data. It allows for real-time data processing, which means we're not just transferring data from point A to point B. We're actually really doing something with the data. It could be adding more to the data. It could be stripping out content from the data. It could be just modifying what's in the data. That's the whole point behind stream processing, is we need to actually manipulate the data in the process of transferring the data as well. Now, it does require the producer of the data to be continuously writing the data, and also the consumer has to be continuously doing queries for the data as well. That's going to be a big important part of the stream process itself. This isn't typically possible with traditional databases because the database software has to actually use the indexing process before storage, and that actually takes too much time, so the streaming process can't be run in that kind of environment. So let's talk about some stream processing solutions before we get into some more details about stream processing. So we can actually use stream processing to do a massive amount of data changing at a very small performance impact. We can provide analytical operations. We can process data to provide alerts. We can respond to a massive number of user queries really quickly. We can integrate data from different sources, aggregate data from different sources. And then we can also use this for rapid system deployment. So let's talk about a few use cases here. You might use this type of stream processing for things like risk management, for e-commerce, for monitoring network activity. You also might use it for market analysis, fraud detection, dynamic processing updates, and also surveillance. So as far as Kafka stream processing is concerned, it is possible to perform this with traditional producers and consumers, but most likely what you're going to do is make use of the Streams API, which we'll see later in lesson number 11. Hello, and welcome to Lesson 4 API Overview. In this short lesson, we'll explore some of the basics of the producer and consumer APIs. The goal of this lesson is to start exploring the Java libraries that are used while creating Kafka applications. In this next session, we're going to talk about API overviews. And we'll first start off talking about the producer API. Now, before I jump into the content, let me kind of highlight something that I think is going to be important. I don't want this training video session to all be about just Java. So I'm going to focus more on the theories and applications of Kafka, and then occasionally jump into some API programs that use Java as the source code itself. Now, the reason why I don't really want to focus too much on Java is because, number one, I can't really assume that everyone who's watching these training videos knows Java really well. And in fact, you may not even be using Java for your language to talk to Kafka. You may be using something different, like Python or Perl or any number of the other languages that are available for Kafka implementation. So while I will show you some examples in Java, because that's probably the most popular language for creating Kafka consumers and producers, I don't really want to make that be a main focus of the training videos themselves. And I'll try to keep the program simple, so even if you don't know how to program in Java, as I step through the code and explain it, it should make sense overall. Now with that said, if you're going to create a producer using Java, there are 3 API libraries that you want to be aware of: the Kafka producer, the producer, and producer record libraries. Those you should actually import into your code. And then once you've done that, you can put together some code that looks like the following. So let's just step through this and look and see one line at a time or one section at a time what this program is going to do. The first thing we have is this private properties, myprops equals new properties. So this is going to create a object that's based upon the properties class, and we're going to call the object myprops. The purpose of this object is really to populate a whole bunch of properties that are going to be used to start up the Kafka producer. So later on when we use the Kafka producer, it's going to use some properties that we'll define, and the properties are defined by these put statements, as you can see right here. So we're not going to worry right now, by the way, what these different properties are. You can probably guess some of them by looking at them. Like for instance, the Bootstrap servers has a couple of server names, in this case localhost, and port names as well. Those are the Kafka brokers we're trying to communicate with. But don't worry too much right now about what these different properties are. When we get into the section on creating producers, we're going to talk about what all these things are. So we'll see what key serializer is, what value serializer is, what retries, and all these other properties, and some other ones we'll talk about as well. But anyway, this just generates all the properties that we need to create a producer. And then to create the producer, we'll use the new method for the Kafka producer class. Now you can see one of the things that's being passed in here is the myprops property, which will define what kind of properties we want to use to create that producer. So at this point in time, we now have a producer. We just have to start creating some records. And you will use different techniques to create the records, but essentially the code is going to look like this. You'll create a producer record, and the producer record will be based upon the new method, and we'll pass in some values. Like you see, customer phone, Sarah, 155555555. Those are the bits of information we need to use to create the record itself. And then after we create the record, we need to send that record to the Kafka brokers, and we do that by using a try block. So basically a try block is going to go through the process of trying to send something to the producer by using producer.send, and if it succeeds, everything's fine. If it can't send a producer message, then we'll do a catch and have an exception of some sort. In this case, it's going to print out a stack trace message as a result. I provided a link there, by the way, if you want to see more information about the Java producer. You can go to that URL and get some more information. You can find that also just by going to the documentation for Kafka and then following the links to see the producer. I also want to give you an example of a Python producer. So in this case right here, we need to first load up the Kafka producer library for Python. The next thing we have to do is specify the different types of parameters that we're going to use to create this. So we're going to use slightly different format, as you can see here. We'll use Kafka producer and pass in some parameters that we want to utilize for the Kafka producer. And then once we've actually specified all the parameters that we want to use, then we can use producer.send. So it's a very similar type of functionality that we send off this information. It's a little bit different format overall, but you can see it's very similar to the way that things are done in Java as well. So this next section, we'll go through the consumer API. And again, we're just going to go a quick run through what's involved in creating the consumer API. Not worry too much about the details quite yet. But there are 3 different API libraries that if you're using Java that you want to load or import. So Kafka Consumer and Consumer Record. And an example of what you might do to create a consumer is you first create some properties. This is very similar to the technique that we use to create properties for the producer. We populate the properties. And again, very similar type things that you're going to put together here. Slightly different. There's going to be some other values that you might have here, like group ID, for example, was not included in the producer example. And then lastly, we want to start actually creating the consumer itself. That's what the Kafka consumer is going to do. We specify the properties, and it'll start reading from the consumer at that point. Hello and welcome to Lesson 5, Installation and Configuration. In this lesson, we will discuss how to install and configure Kafka. We'll start by discussing hardware and operating system considerations. We will then cover the installation of Zookeeper, a separate software tool that's needed for Kafka to perform correctly. Lastly, we'll cover how to install Kafka and perform some basic configuration operations. In this next lesson, we'll talk about installation and configuration of Kafka. And we'll begin talking about some hardware considerations. First thing you need to talk about is the difference between a development environment and a production environment. And development environment, typically you can install it on a laptop, like I've got on my system right now. Memory isn't really the largest issue that you'll deal with. And you probably want to consider using virtual machines, which is I'll be doing myself. The operating system is probably more of a critical choice than anything else. I highly recommend that you use Linux as the operating system. In your production environment, you want to think about hardware a little more carefully. Hardware is going to have an impact on how your Kafka implementation works. And definitely clusters will have an impact as well. You probably want to consider benchmarking, doing some tests to make sure the speed and the throughput of your Kafka brokers are up to what your standards are going to be. So let's talk about a development environment. Again, I suggest that you use virtual machines. For testing purposes, 3 virtual machines works the best. You can have a Kafka broker on each virtual machine and test it out. You probably want to limit the extra software that you install on the virtual machine. There's really no need for a graphical user interface, for example. If you're installing Linux, I consider not including that typically on a development environment. You want to have at least 4 gigabytes of memory for the virtual machines for testing out as well. On production machines, the first thing you want to consider is the memory on the system. So while the file system is used for storing messages and caching, the kernel's page cache is heavily used. What that means is it'll use some memory for some disk caching, including the Java heap space. Typically, each heap space is going to be about 5 gigabytes overall, and the file system cache in total is going to be about 30 gigabytes of space that you want to allocate on your system. Typically, your buffer storage is going to be about 30 seconds. So when it's buffering the information, using the page cache, it's going to actually use about 30 seconds worth of information there. So your formula to figure out exactly how much memory you want to have is going to be the write throughput times 30. Typically, standard 64 gigabytes is what you need for an operating system that you're going to run Kafka on. But you can get away with a minimum of 32 gigabytes, depending upon how much activity is happening on that Kafka broker. As far as CPU is concerned, this is actually not nearly as critical as memory or hard drive considerations, but it's more important that you actually focus on the number of core CPUs than CPU speed. Typical common cluster configuration is about 24 CPUs. Storage space is definitely going to be a bit of an issue. You really want to consider a lot as far as how you want to store the information. File system is used for storing caching, as I mentioned before. You may want to consider multiple hard disks. If you have multiple hard disks, especially if they're on their separate controller cards, they'll be faster overall. Speed is really going to be important, so if at all possible, you want to use solid-state drives. RAID can be helpful, but keep in mind that RAID is typically used for redundancy. So if one RAID device goes down, another RAID device can take over, but Kafka has its own redundancy. There are some considerations you want to think about. RAID is typically a little better at load balancing, especially hardware RAID, but keep in mind software RAID may actually slow things down a little bit. So if you're using the kernel to perform the RAID operation, that might have an impact. RAID does sometimes result in a write throughput performance hit, and almost always RAID is going to result in less available hard disk space. You may want to consider multiple directories on separate disk drives as well. You definitely want to avoid any type of NAS or network attached storage device because going across the network is going to have a performance impact when you're storing information for Kafka. The last thing you want to consider is your network. So obviously, the faster you can possibly have, the better it's going to be. You definitely want to keep all your clusters in the same data center. Any type of distance between the clusters can cause problems, including latency issues, and those latency issues may cause problems as far as debugging is concerned, benchmarking is concerned, and resolution too. So in this next section, we're going to talk about the operating system and Java installation process. So before you choose which operating system that you're going to install, you may want to take the following into consideration. First of all, the standard operating system that you normally run Kafka on is going to be either Linux or Unix-based operating system. I recommend a file system that's either ext4 or XFS. File systems play a really big role in performance, so you want to tune the file system. For example, you probably don't want to have the option of A time, which is access time. Access time is an option on file systems that whenever a file is accessed on the hard drive, it updates a timestamp on that file. So things like that you want to try to avoid as much as possible. There's not a really big need to have an access time feature. So when you mount the file system, make sure you use the option of no A time. There's some other mount options you can look at to further fine-tune and limit the number of writes to the hard drive, but that's one right off the top of the bat that you probably want to disable. There are no file system dependencies, which means it doesn't really matter if you use ext4, XFS, Btrfs, or some of the other file systems that are available in Linux, but you probably want to avoid network file systems. There's a note in documentation on Kafka that says you want to avoid using shared mount drives and network drives. There's some type of index failure on the file systems because Kafka uses something called memory map files to store the offset index, and that's been known to have issues with network file systems. Not to mention the fact that any kind of network file system is going to have a performance impact because any kind of data is going to have to go across the network in order to be able to store on the network, so you want to avoid that at all possible. You could consider using Microsoft Windows. It's not really supported right now, although there are versions of Kafka that run on Microsoft Windows. It is something I don't recommend since Kafka is really originally written to be written on Linux, and all the examples I'll show you throughout the entire video series is going to be based on Linux operating system. You can also use Mac OS since it's a Unix-based operating system as well. Now, if you choose to use XFS for your file system, one thing you should know is that XFS has an auto-tuning feature, so quite often you probably won't have to make very many changes to the file system features and capabilities, but there are a few mount options that you may want to consider using when the system mounts the XFS file system. One is to make use of something called large I/O. This is really good for large disk writes, which happens quite often in Kafka. And also you probably want to make use of something called no barrier that disables write flushes, which should make the entire process a lot faster as well. ext4 file systems have some more tunable options that you may want to consider. You first of all may want to consider disabling this feature called journaling. So journaling is the process of whenever an action takes place on the file system, an entry in the journal is added to specify what that action was. And the point behind the journaling file system is when the file system is improperly unmounted, like maybe the power goes off in the system and then the machine boots back up again, that file system is going to have to be fixed. In order to be able to fix the file system, it could go through the entire file system, probe the entire thing, and find all the problems with it, or it can make use of this journal to recreate the things that were lost in the file system, things that didn't actually get flushed to the hard drive. It can recreate those. So it does speed up the process of recovering from a file system failure during the boot process. The problem with a journaling file system is every single time an action takes place on the file system, a write occurs onto the drive. And so if there's a lot of activity taking place on the file system, that's going to end up with a lot of writes occurring on the hard drive. And we want to limit writes as much as possible. So you may want to consider disabling journaling. It won't have an impact necessarily on data loss, so when you reboot the machine, it'll still recover all the data as it would normally, but it would take a lot longer to recover the data. So that's something you may want to consider as a trade-off. Some other mount options that you might consider to include in the ext4 file system is there's one that actually is going to reduce the latency. It's called data equals write back. So include that as your mount option. And if you're going to use that option, you can actually use no BH that's used in conjunction with data equals write back to further reduce latency. We can specify commit equals and then give a second value. A lower value helps reduce crash data. The idea is typically that the stuff that's actually stored in memory, things that would actually be written to the hard drive, like your metadata, things like file system ownership or file ownership, directory ownership, permissions, things like that, they're stored normally in memory. And there's an option called commit, where commit equals, like say 30, means that every 30 seconds those things are flushed to the hard drive. So if you're going to disable journaling, you may want to say commit equals a lower value, maybe 15 or 10 or something like that. That's going to help reduce any kind of loss if this file system fails, and also reduce the amount of time it takes to boot the system up as well. You can also use an option called deallocate, provides better throughput overall. There have been some instances where it may briefly lock the file system, but it does provide better throughput overall. So as far as kernel parameters are concerned, these are set in the etc syscontrol.conf file. A couple of ones that you may want to consider: VM swappiness, set that to a value 1. That will limit swap space use. You can also increase network speed by setting the net.core.wm_default and net.core.rm_default to a value of 131,072. This is about 128 kilobytes overall in space. And then we can also set the netcore, WMmax, and RMmax values to about 2 megabytes in space overall. That would actually increase network speed as far as how it reads and writes data across the network. There's also some parameters that have to do with what they call dirty paging. As you can see, there's quite a few of them here, and I'm not going to go through every single one of them. I do recommend that you spend a little bit of time learning about these different settings and what you can actually do with them. I'm just going to talk about one just for a demonstration here. You'll notice that one of the values on the screen right now is vm.dirty_background_ratio. It's set to a value of 10. So the idea behind this is we have these things called dirty pages. They're basically pages in memory that need to be written to the hard drive. And what we're saying by using a value 10 here is that we won't allow the percentage of dirty pages to go above 10%. So if you had a machine that has 64 gigabytes of RAM, for instance, you can have at most 6.4 gigabytes of dirty pages. And at that point, once you go above 6.4, there's a utility called the flush utility that will flush all that stuff to the hard drive and clear up that space. Now, one of the advantages of getting rid of these dirty pages on a regular basis is it frees up more space for system caching, and that would be better on a system that has Kafka installed. So there's some other ones you want to look at here as well, but I think that give you an idea that you can actually fine-tune these things, do some benchmarking too, see how it's going to have an impact on your performance of your kernel and how it handles the dirty pages. So now as far as Java is concerned, I do recommend you install the full Java development kit. A lot of distributions already have OpenJDK installed, and that's fine. It could be either the OpenJDK or the JDK that comes from Oracle. Either one's fine. If you want to see if you already have it installed, so maybe you don't have to install it all, you can just use the command java-version. And if you have it installed, you actually get back output. Looks like this right here. If you don't have it installed, then to install it, what you probably want to do is download it. In this case, I'm downloading it from Oracle itself. And then you can extract the files. And then after you extract the files, you probably want to move it to the correct directory. So whatever directory you want to store it in, and modify your path so you can find that. Put it in user/local/bin, for instance. And then there's a command called alternatives. Alternatives allows you to specify the location of where the Java software is. In this next section, we're going to talk about Zookeeper installation. Now, you may be wondering why we're installing this thing called Zookeeper. Zookeeper is really an important part of Kafka. It keeps track of what we call metadata that has to do with the Kafka brokers. It also keeps track of the communication between the Kafka brokers, the consumers, and the producers. So it's an important element. Now, it itself is a large topic. We're not going to go through a lot about talking about how to configure Zookeeper, all the different settings that are possible. We're just going to talk about the essentials that you need to know to set up Zookeeper for Kafka. It's definitely a topic that you probably want to explore more about. But for what we're going to talk about in this video training course, this should be enough to get you up and running, at least to get you to the point where you can actually use Zookeeper in conjunction with Kafka. So the first thing to point out here is there's several different installation methods. If you're working on a Debian-based operating system like Ubuntu or MintOS, you can use a command called git apt. You do git apt install Zookeeper. If you're running on a Red Hat-based distribution like Fedora, Red Hat Enterprise Linux, or CentOS, you can either use the command yum install Zookeeper, or some of the newer versions of the Red Hat-based operating systems make use of something called DNF. It's very similar to the yum command, but you do a DNF install Zookeeper. You can also do a manual installation. I'll demonstrate that in a few seconds here as well. So if you're on a Fedora-based operating system like I am right now, to install Zookeeper, you run the command yum install Zookeeper. And so what it should do is go down and download all the packages for you. I didn't choose the -y option for yes automatically install because I wanted you to see that it's going to install not only Zookeeper, but a bunch of other software packages that come along with Zookeeper that are dependency packages as well. So if I type in Y for yes, it'll install all the packages that are necessary, download them onto my system, and install them for me. Depending upon how fast your network is, this may take a long time, but they're pretty quick on my system right now. And once the installation is complete, you can configure Zookeeper, and we'll talk about how to do that in a future slide. So now if you're on a Debian-based system like this Ubuntu operating system, the command you want to run is apt get install Zookeeper. And this should download and install Zookeeper for you automatically. Now, I don't anticipate you having to do a manual installation. It's not a very common thing to do, but if you're in a situation where you can't use the yum command or the apt-get command on Debian and Red Hat-based systems, you can actually use this technique. You can manually download Zookeeper, so just find the installation location online, and then use the tar command to extract it so it comes in a compressed tar file. So the .tar.gz indicates it's been compressed and merged together with the tar command, and then just move it to the location where you want it to go. Now, as far as Zookeeper configuration is concerned, there are a few things that you probably want to consider at least looking at and possibly changing as well. There is a zoo.cfg file that you can modify. Normally it's stored in the etc Zookeeper directory, but if you did a manual install, it might be in /user/local/zookeeper/config. But in any case, you probably want to look at the example file that's provided and make some changes to this file. Typically, it's not a very large configuration file. There's a few things you may want to change in there. One thing you may want to change is the tick time. So the tick time is in milliseconds. So if you did something like 2,000, that would be like 2 seconds overall. And the idea behind the tick time is basically the time that it uses to keep track of things that are on the system. For example, it sends these heartbeat messages to the Kafka brokers, the consumers and producers to make sure they're still active, connected to the system. It'll also do things like use timeout values, so session timeout values will be set to 2 seconds if you set your tick time to 2,000. The other thing that you want to know about is a data dir. So data dir is going to be the directory where it stores the data for Zookeeper. At least you should be aware of where the data dir is, because you may want to go in that data dir and either look at some files or place some files in the data dir directory. And then also you want to use the client port to specify what port it's using to listen on. Typically that's going to be a default value, but you can change it to something else if you want to. So a typical example configuration file, like on my Ubuntu system, looks like the following. I use a grep command, by the way, to just show you the actual settings. There's some comments in the files as well. In fact, there's actually a lot of comments in there. But by using that grep command, I was able to just filter out all the comments and the blank lines to display just the settings. So you can see my tick time example is set to 2,000. There's some other values in there as well that I haven't discussed, like a init limit and sync limit, but you can see the data dir is going to be storing the information about the Zookeeper inside of var lib Zookeeper, and then it's going to listen on port 2181 as in this case right here. Once you've configured Zookeeper, and in fact in some cases you just leave it the default values, you can go ahead and start Zookeeper up. You can start Zookeeper by specifying the path to Zookeeper. So in this case it's down in /user/share/Zookeeper/bin/zk server.sh, and then you pass in the argument of start. And that should start up the Zookeeper. You can see it started right now. If you want to test out Zookeeper to make sure it actually is responding, there's a really cool way of going about doing that. So to test that, you can actually make a telnet connection to it. So you can do a telnet. I'm assuming that you're going to run Zookeeper on a local system, but you can use an IP address instead of localhost. And then the port number that you want to connect to is going to be 2181. So here's an example where we did telnet to localhost 2181. And then once that's successfully connected, you see it says connected to localhost in the third line down. And then it gives you a place where you can type in commands. There's a bunch of different commands you could do to interact with Zookeeper. The srvr gives some basic information about the server. So you can see that the srvr command was run here, and you can see information that came back as a result. Again, it's just testing to make sure that Zookeeper is up and running and working properly. The last thing we'll talk about just briefly here is Zookeeper ensembles. Now again, Zookeeper is a fairly large topic. Ensembles actually is a large topic within Zookeeper itself. You can think of ensembles as kind of like a Zookeeper cluster. So we talked about Kafka clusters before. You can have Zookeeper clusters as well. They just have a different name. If you're going to make a Zookeeper ensemble, that means a certain number of Zookeeper servers that will actually be talking to your Kafka clusters. You probably want to use an odd number of servers. Also, you need to include all of the servers in the ensemble in all the Zookeeper's zoo.cfg file. So for every single instance, so you may have, like, say, Zookeeper running on 5 different servers. Each of those 5 different servers, you'd have a separate instance running, a separate zoo.cfg file, and you'd have to specify all of the servers that were in that ensemble. That's how they know how to talk to one another, by using this setting right here. So here'd be an example. I'd say like server.1, and then I have the server that I'm actually communicating with, zoo server 1, and you can see it's got the port number listed there as well. You will also make a file inside of the data directory. So this is how the Zookeeper knows what server it is, whether it's server 1, server 2, server 3, or whatever. And it's going to be a file called myID. And the only thing that's going to be in there is going to be the ID for the local host. So if I was on server 3 of my ensemble, I'd create a file inside the data directory called myID, and the only thing I'd have in there is the value of 3, and that's it. Again, there's a lot more to Zookeeper ensembles. I would highly recommend, if you want to learn more about those, explore those to see how they can actually impact how your Kafka brokers work and your clusters work. But that just gives you a basic idea how to set up Zookeeper and some of the configuration settings that you may want to look into. In this next section, we're going to talk about how to install the Kafka broker. The first step in installing the Kafka broker is to download it. So you can see the URL there. Go to kafka.apache.org/downloads. You have a couple choices of 2.11 or 2.12, depending upon what version you want to use. They recommend 2.11, but you can use 2.12 if you want to. Once you've downloaded the file, you can extract it by using the tar command. It's a compressed tar file. So you're going to use the command tar-xzf. Z is to uncompress the tar file. And when you're done, you end up with a directory that has all the Kafka installations in it. You want to move that to whatever location makes sense for you, typically /user/local, but use the mv command to move it to that location. And then once you've moved it, you can start up the Kafka broker by using a command called Kafka server-start. Now, one of the important things to point out here, and I'll demonstrate this in a few seconds, you also have to make sure that you start the Zookeeper software program first. But after you start up Zookeeper, you can start up Kafka. So in this case right here, the path to wherever you have Kafka installed, underneath that there's a bin directory, and then there's that Kafka server-start.sh. And then you do have to specify a path to the server properties file. I'll give you a demonstration of the server property file in a few moments here, and talk about some of the basic configuration settings you can have in there as well. Now, one interesting thing about the way this command runs, it's really good for a situation where you're testing out Kafka. So in a development environment, it automatically runs in the foreground. Now, the reason why that's a benefit is because you can see messages pop up inside of the output of this command. If you don't want to see those messages, if you want to run this command in the background, then choose to use the option -daemon. That'll place it in the background. The advantage behind that is it won't be running the foreground. You won't have to keep that terminal window up and running, because if you close a terminal window, it's likely going to close any program that's running in the foreground as well. So that's one advantage of using that. But if you do place it in the background by using -daemon, then you don't get to see messages that pop up that might indicate what's going on with your Kafka server and why it may not be performing properly. If you put it in the background, then you can stop it by using the Kafka server-stop command to stop that Kafka server. And again, there's a path to the properties because you could have more than one Kafka server up and running at a time. In fact, we'll demonstrate that a little bit later on. I'll actually start up multiple Kafka servers on one system. So for it to figure out which Kafka server you want to stop, you need to specify the properties file. That properties file gives information about which server that you want to stop. And each Kafka server will have its own property file, as I'll demonstrate later on as well. If you don't run in the background, so you don't use that -daemon option, then all you have to do is go to the terminal window where it was running and just do a Control-C. That Control-C will stop that program. So what I've done is I've already installed Kafka, and I just want to kind of explore what's going on inside this directory so you understand what's available to you and what kind of things you can do with the Kafka installation. So if you go down the Kafka installation directory like I already am on this Fedora machine, and you type in the command ls, you'll see there's several directories here that are useful. One is site docs. So let's go down to site docs for a second here. You notice site docs contains a tar zip file. If you untar and unzip that file, you'll have all the documentation available on the local system. Typically, I tend to use the documentation online, but if you want it locally available, this is actually what you want to do. Let's go back up one level. So now at the top level here, we also have a bin directory. If I go down into the bin directory, you'll see a bunch of different scripts you can execute, including that Kafka server start and stop script that you can use to start and stop the Kafka server. Just a little side note here, there's also a built-in Zookeeper that comes with Kafka. I know in previous lesson we actually installed it as a separate program, and that's one way you can go about doing that. But you can also make use of the Zookeeper that comes with Kafka itself. So if you look at my screen, you'll actually see that there is a Zookeeper start and stop operation, which is very similar to the way we started Zookeeper in the previous lesson as well. I use this for just demonstration purposes, so you know how you can use that. And if you don't want to install your own separate Zookeeper and server, this is a perfectly fine way of going about doing that. Let's go back up one level, and then go down into the configs directory. So in the config directory, you'll see there's different config files. We can use these in most cases by default. For example, the Zookeeper properties can be used to start up a Zookeeper server. Obviously, if we want to fine-tune it and have it work and behave differently, we'd want to make some changes to it. But the one that's provided by default works just fine for demonstration purposes and testing purposes as well. There's also a servers.property file. Again, that's something you may want to explore and modify to fit your needs, but we're going to use this just as it is for this next demonstration. So first of all, if I want to see how this all works, I first need to start up Zookeeper. And so remember, Zookeeper is underneath the bin directory, so I could do a Zookeeper server start command. And I need to specify the properties here. Now, if you don't try to run it just like as it is right now, you'll see we get a message saying, hey, you need us to provide at least properties. Remember, the -daemon says run in the background instead of the foreground. So I need to specify properties, and again, there is a default property config file. Underneath the config, there is a Zookeeper file that we can use for this demonstration. So I press enter here, it should start up Zookeeper. You can see that Zookeeper's up and running. It's bound to port number 2181. So at this point in time, it's listening on port 2181, which is the default port for Zookeeper. Now I'm going to leave this up and running in this window. Let's actually put a few new line characters so you can actually see something happen in a few seconds. I have this second terminal window where I'm going to start up Kafka Broker now. So for this, I want to run bin/Kafka server start. And then again, I need to specify the location of the config file I'm going to use. We'll talk more about what's exactly inside of this config file, but I'm just going to use the default one that comes with Kafka. And now, once I press enter here, you're going to see this interaction happen between the server for Zookeeper and Kafka Broker. So you see things happening on both windows as they start to communicate with one another And the broker basically registers itself with the Zookeeper. As you can see, there's the interaction between the two. So that's a demonstration how we can get Kafka server up and running. And we'll talk about a little bit later on how we can start sending information to the Kafka server. I'll just leave it up and running right now so we can use this as a further demonstration. Okay, so as far as the Kafka configuration is concerned, remember we're going to modify the servers.property file. In fact, each broker is going to have its own servers.property file. So as time goes on, you add more brokers, you'll end up with like a server1.properties and a server2.properties and so forth. There's some basic settings that you want to know about inside this file right here. Each broker has to have a unique ID. So one of the things that we'll have inside of the servers.property file is a setting that says broker.id equals and some kind of numeric value. So the first one would probably be 1, the second one would be 2, the third one would be 3, and so forth. Also, we need to specify a port to listen on. So each broker has to have its own separate port to listen on if they're all running on the local machine. Now, if you have brokers that are on different machines, that's fine. They can use the same port number because each system has its own port numbers. But if you're going to do like I'm going to demonstrate a little bit later on and have multiple brokers on just one single local system for testing purposes, then make sure you use different ports for each of those broker IDs. You also need to specify a location where you want the log files to be stored. And the log files, remember, are really the partition information. We call them log files, but when you start writing stuff to the partitions, they get stored in these log files. And each of the brokers should have its own location for log files. So for broker ID number 1, maybe you put it underneath /temp/Kafka1. For broker ID number 2, you put it on /temp/Kafka2 and so forth. It's really up to you as far as where you want to put the files. If you're familiar with the Linux operating system, you know that the /temp directory is for temporary files only. It's an okay place to put these files in a development environment because you probably will have downtime in your development environment where you're not working on the system and you don't care if those files get wiped out, because what happens is there's a cron job that runs on a regular basis and goes down in the temp directory and removes any files that haven't been used in a while. So on a development environment, that may not be that big of a deal. And actually, technically, a production environment, it may not be either, because if your Kafka server is up and running 24 hours a day and constantly getting data, then that might be an okay place to place them as well. To be honest with you, most people, though, don't put it in the temp directory. They put the files instead in some directory underneath the var directory. The var directory is quite often a separate partition on the file system, so that partition may actually have a larger amount of size available than the temp directory structure will. And also, I think I mentioned earlier that you want to consider possibly using separate physical devices as well. So if you're using several physical devices, they're going to have separate mount points in the Linux operating system. So each mount point might be the place where you actually put the Kafka log files. So in this next section, we're going to talk about how to configure topics. So the first thing to point out here is there is a command line tool that let you create topics. Just for this demonstration, we're going to use kafka-topics.sh. This is a tool that's available underneath the bin directory in your Kafka installation. Now, when you run this tool, you're going to use the --create option that will create the topic, but you also have to specify where Zookeeper is. So when the topic gets created, we have to actually specify the host name and port number of Zookeeper. It looks a little funny, I know, on the screen. The -- at the end of the first line should be right next to Zookeeper at the beginning of the second line. So you'd say --Zookeeper, and then the host name or IP address, in this case it's going to be localhost, followed by colon, and that the pound sign is going to be replaced by the port number, like 2181, for example. The next two options, I don't want you worried about too much about. I'll go through them really quickly here, but we will talk about replication factor and partitions in more detail later. But if you set your replication factor to 1, you're basically saying there's no redundancy here. So all the information is going to be stored on the partitions that I specify, and if one of those partitions goes down, we're going to lose all our data. That's actually okay in a testing environment. Obviously, in a real-world environment, you want to have a replication factor of greater than 1. Typically, it's like either set to 2 or 3. so that if one of the partitions that you're writing to goes down, we have other backup partitions that will take care of the data and continue to provide the data to consumers. In this case, we're also going to only use one partition, so we're going to say dash dash partitions equals 1. If you said dash dash partitions equals 2, that means the data would be split between two different Kafka brokers. Each one of them would have a partition where it's going to store the information. Again, we'll talk more about replication factor and partitions later. We need to specify those values now because that's how you actually go about creating a topic. You have to specify the partitions that you want the topic to be stored on and the replication factor as well. But it's actually discussed in more detail in another lesson. And then you specify dash dash topic and whatever you want to call the topic. It's entirely up to you as far as what name you want to provide it. You should also note that there's a command line tool, or an option I should say, to the command line tool Kafka Topics that will let you list the different types of topics that you already have created. So obviously when you first get started, there will be no topics at all, but if you use dash dash list after you create a topic, and you specify the Zookeeper server's host name, IP address, colon, and then the port number, you'll actually see the lists that are available. I'll demonstrate that for you in a few moments here too. Now, another cool thing I think about the command line tools is once you've done this, you're going to probably want to test it out. You want to see if it's actually working properly. And one way of testing this out is to actually create some software that has a producer and some software that has a consumer. But we haven't really gotten to that point yet. We've gone through some basics about creating producers and creating consumers, but there's some more details we want to know about that before we actually start getting more heavy into the coding. So instead of doing that, there's a cool tool called Kafka-console-producer.sh, which will create basically a command line producer. So you can actually send messages to the topic by using this command line tool. Once it starts up, it'll give you like basically a blank line where you can start typing some messages in, and those messages will be sent to the topic that's specified. So for this to work, what you do is you run the command. It's going to be down the bin directory underneath the Kafka directory, and then you specify dash dash broker dash list. So you need to specify the broker or brokers that are available. So these are the Kafka brokers, not the Zookeeper hostname and port number, but the Kafka brokers instead. You could do more than one, but for this demonstration purpose, we only need really one here. That will be localhost followed by whatever the port number is for localhost for that particular broker. And I'll show you how you can figure that out if you don't know it off the top of your head. And then you specify what topic you want to start sending messages to. In addition to that, there is a nice little utility that lets you view the results. So we can use Kafka-console-consumer.sh. For this one, we have to specify the location of Zookeeper. That's why we have dash dash Zookeeper, and then the location of the Zookeeper and the port it's listening to. And then we have to specify what topic we want to start reading from. So probably the topic that we created in the first operation. We also need to specify where we want to start reading from. So we can start reading from message number 5 if we want to, but if you use dash dash from beginning, it'll start reading messages right from the very beginning. Okay, so let's see a demonstration. I've left my Kafka broker up and running, and also the Zookeeper up and running. You should still see them on the screen right now. And what I'm going to do next is go through the process of creating some topics and just showing you how those topics actually can be written to and read from by using the command line Kafka producer and Kafka consumer. So let's start up another terminal window first. Make that a little bit bigger. And I'll switch over to my root account for this demonstration. And let's go down to /user/local/Kafka. All right, so the first thing I'm going to do is go ahead and create a topic. So down underneath the bin directory, there is the Kafka-topics.sh. We'll use dash dash create. We'll use dash dash Zookeeper. And it's on localhost, port number 2181. We'll do a replication factor of 1 and 1 partition. And we'll just make up a topic here called my topic. So there we go, we have a topic. And actually, if you look really in the background here, you can see that it created the topic here. There is the topic that was created right there. And we created a partition from that. So my topic -0 was the partition. So that seemed to work just fine. We can always double check this though. We can run bin kafka.topics. .sh, and we could use the -- list option, and then -- zookeeper, and then again localhost port 2181. So you can see we only have one topic so far, and that kind of makes sense. We just started up this Kafka cluster a little while ago. So the next thing you want to do is demonstrate how we can create the producer. So for this one right here, you have to know the IP address or host name of the broker and what port it's listening on as well. Now I know it's on the local system, so that's pretty easy, but how could I figure out what the port number was if I didn't know off the top of my head? And this comes back to remembering that underneath the configs directory, there is a server properties file, and in the server's property file, there is a port number specified. So it should be 9092. Let's just do a search for 9092. Yep, so it's 9092 in this case right here. So what I'm going to do is run the Kafka console producer, and I'll say broker list localhost 9092. And then we just need to specify the topic that I want to write to, and that'll be my topic. So at this point in time, that little prompt means I can actually start sending messages to my topic. So I'm going to have to send in some information like this is the first message, second message, and third message. Of course, I probably want to make sure those are actually being received. So what I'm going to do here is, let's make this smaller here so we can actually see that screen, and open up another terminal window and go down to /user/local/Kafka, and let's run underneath the bin directory the Kafka -consumer console program. Again, we have to use -- zookeeper localhost and port 2181, and the topic we want to read from. And again, we want to read from the beginning, so we'll use -- from beginning. Now, the moment I do this and I press enter, I should start seeing some new messages appear inside of this window right here. It should read first message, second message, and third message. So let's test that out. So there are the three messages right there. First message, second message, and third message. And if I want to test this out even further, I can go back into the producer window and type another message. I'm not very clever in my messages, by the way. And you can see in a few seconds, or less I should say, you'll see the fourth message appear right down here as well. So that's a demonstration of how you can actually test to see how this stuff is working. You wouldn't normally use Kafka console, producer, and consumer on a regular basis, but before you actually start building out all the software that you're going to for your producer and consumers, it's kind of nice to make sure that this actually works. So this is just a quick little way of demonstrating that you can actually send messages and that your topics are working and that your Zookeeper is working properly and your clusters are working and all of that kind of stuff as well. And we'll go back and see a little more demonstration about this later on, because we'll be able to use this technique to also demonstrate how this information is stored in different partitions and how replication works and other factors as well. Okay, now it's time for you to get some practice. In section 5.6, we're going to do the lab exercise. I won't go through an answer for the lab because the answer could vary depending upon several factors. You're going to be able to choose what operating system you're going to install Kafka on and some other features as well. So I'm just going to give you some steps that you want to go through, and how you go about solving those steps is entirely up to you. So the first thing you want to do is install an operating system of your choice. I do suggest Linux, but if you want to try to make this work on a Unix-based platform or Microsoft Windows, feel free to go ahead and try that as well. Also install JDK or confirm that it's installed. Make sure you install Zookeeper and confirm that it's installed as well. And then install Kafka. I recommend 2.11. After you install Kafka, create a topic. After you start up, of course, the broker and the Zookeeper servers. And then start a producer. And then test out that the consumer can read from the producer. Hello and welcome to Lesson 6, Clusters. Clusters are a key component of Kafka. We'll first explore the purpose of clusters and then discuss the process of replication. We'll then complete this lesson with a demonstration on configuring clusters. In Lesson 6, we're going to talk about clusters. And we'll start off by talking about what Kafka clusters are. So it all starts off with this broker. Remember, a broker is a single Kafka server. And keep in mind that the idea and purpose behind a broker is to receive messages from producers and allow consumers to retrieve the messages. A Kafka cluster is really a collection of brokers. And the brokers are going to accept the messages from the producers and then allow the consumers to retrieve those messages. And the way this works is that there's a software program running called Zookeeper. It's a separate application from Kafka, and we've already seen how to install it and some basic configuration in a previous lesson. But the purpose behind Zookeeper is it keeps track of all of the metadata that's corresponding with the brokers, the consumers, and the producers. So the metadata will be information about like what kind of topics there are, which consumer is going to read from which partition, and other key components like that. Speaking of partitions, keep in mind that a Kafka broker can contain one or more partitions, and each partition is going to be used to store information from a topic. So when a producer sends information to the cluster, it doesn't really send it directly to the cluster. It actually sends a message to the topic. And then that topic is going to have several possible partitions that the data is going to be stored in. And it's going to be up to Zookeeper to decide which message goes to which partition. And there are several different approaches that we'll see as class continues on and how that can be determined. One way is a round-robin approach, in which we have one message go to one partition, and then another partition, and then a third partition, and so forth. So in this next section, we're going to talk about replication. It's something we've discussed a couple times in the past lessons, but this was where we get some more detail about how this actually works and what kind of concepts you want to be aware of when it comes to replication. So we see a diagram like this in the past with the producer sending information to the Kafka brokers and the cluster, and the interrelationship between the producer, the consumer, the cluster, and Zookeeper as well. But let's say we have a situation where we've created a topic that has a replication factor of 3. Now what that means is we're going to have a primary partition and then 2 backup partitions as well. Data will be basically redundant across 3 different partitions. So when the message gets sent to the cluster, a primary partition will store the information, and then there'll be 2 other partitions that have backup copies essentially of that data. As more information gets sent to the partition, there'll be more backup copies being made as well. Now the point behind this is if that primary partition were to go down, become unresponsive, this data is still available in the backup partitions, and in fact, what should happen automatically is one of those backup partitions should be promoted to the leader of the partitions. So some key concepts to be aware of. I just mentioned that term leader. So one partition acts as the leader. That's the one that stores the information. And all the other partitions are considered to be followers. The replication factor is the total number of replicas plus the leader. So in the previous slide that I showed you, we had 2 replicas and the leader, so the replication factor was a value of 3. That means when we created the topic, we used that option replication factor is 3. All the writes and re-requests are sent to the leader by default, and then what happens after that is the followers consume messages. Kind of like if they're Kafka consumers, they basically just add the message to their logs, so the leader will send information to those consumers, those followers, and add it to their logs. So all the partitions also had to keep in contact with Zookeeper. We talked about Zookeeper and how it has a heartbeat interval, typically of about 2 seconds. If one of those partitions were to no longer talk to Zookeeper anymore, Zookeeper will tell the Kafka brokers about this, and they'll try to resolve that scenario automatically by introducing new partitions and adding those partitions to the replication. There's another important thing you should know about, and that's the idea of a committed log. So when a message gets sent to the topic for the brokers, it's sent initially to the leader, and then all the followers consume and add it to their logs. but it's not considered to be committed. In other words, it's not considered to be ready for consumers to pull that information until all of the followers have consumed and placed that information in their log entries. So that message is considered to be committed at that point in time, and once it's been considered to be committed, then consumers can actually start reading that information. Now, this is a tricky part, and we're going to talk more about how to deal with this in the next lesson. We talk more about producers, because what's going to happen here is if that message is not properly committed, there's got to be some way for our producers to resend that message so we don't lose it. Otherwise, if it's not resent, then that message could be lost as a result. The last concept that we want to know about as far as replication is concerned is this concept of a quorum. So there's a term called ISR, or in-sync replicas. These are all the replicas that are in sync with the last message from the leader. So if the last message from the leader was like message ID number 25, and we had two replicas, one of them was still on message 24 and one was on 25, that means we have an in-sync replica value of 2, the leader and the replica that's up in sync. If the leader fails, the only followers that become eligible to be promoted to be a new leader are the ones that are in the in-sync replication factor. So the quorum approach behind this is that if a majority of the followers are in ISR, so they're in-sync replicas, then the overall replication is considered to be in good health. Hello and welcome to Lesson 7, Writing Producers. In this lesson, we'll dive into the concepts and code for creating producers, the component of Kafka that creates the messages. We'll focus on how producers communicate with Kafka and how to handle serialization, which is the format of the data itself. Okay, it's time to jump into Lesson 7, talking about how to write producers. And we'll start off by talking about some producer configuration. And as I mentioned before, I'm not going to try to get too heavy into the programming aspect of it. I will show you some Java code, but it's fairly straightforward code. We really want to focus on the concepts here more than anything else, so you can apply it to whatever language you choose to use in your environment. So as an overview, remember that configuration settings are used to modify the behavior producer, and literally there are dozens of different settings available. I would recommend after you go through this video series, you look at the documentation and see some other settings that are available. I'll go through as many as I can, but some are a little bit more esoteric and you may not use them quite as often. But the three that you're always required to include is going to be the bootstrap servers, the key serializer, and the value serializer as well. So let's first talk about the bootstrap servers. This is going to be a list of host and port pairs. The host is going to be the system that has a Kafka broker running on it, and the port is going to be whatever port number the broker is listening on. Technically, you only have to have one host and port. However, you may want to have more than one just in case one of the brokers is down or unreachable for some reason. So an example of what this might look like if you were talking about a Java program is you would specify bootstrap-servers and then a combination of those hosts and ports separated by a colon between the host and the port and a comma between each set of host-port combinations. So let's talk about serializers next. Remember, messages are going to be a collection of keys and values, and while Kafka does make use of byte arrays to send information, the producer can actually use any kind of Java object for the key and the value. So one of the things you want to do is specify to the Kafka broker how to handle this data, this key value pair combination, and we're going to do that by using these things called serializers. So serializers are basically ways to package the data in some way that the producer and eventually the consumer can understand, because the consumer is going to have to know what kind of serialization that was used for this data as well. There is a Java library for this that provides you with some of the common serializations that you need. So org.apache.kafka.serialization.serializer. That interface can provide some serializers. I'll talk about some other more customized serializers that you can make use of later on as well. There are 3 available by default, but again, you can create more if you want to. The different types of serializers that exist by default: you can serialize data by using byte arrays. You could do strings if you want to, which is the example that you'll see in my demonstrations here. Or you can have them be integer values if you want to as well. So we have 2 different serializers. There's a key serializer, that's how you want to serialize the key. And there's going to be a value serializer, how you want to serialize the value. Now keep in mind that for the key, you may want to be like, for example, string or an integer. And the value might be something different. While the serializer for the string might be an integer, the value might be a string, for example. So they can actually be different from one another. Here's an example where they're actually both the same. Again, using some Java code here, we'd say the key serializer is going to be org.apache.kafka.common.serialization.string serializer, and we did the same thing for the value serializer as well. So a little bit more full example. The first line, we actually specify that we want to create an object called myProperties, and we're going to populate that with the properties that we want to in order for the Kafka producer to be created. So the properties we're going to use are going to be bootstrap properties, the key serializer, and the value serializer. And again, there's other things we could put in there as well. We'll talk about a few as time goes on. I'll show you a couple on the next slide presentation, and also as we go through more lessons, we'll talk about some other properties that you could put in here as well. But after we define all the properties, we can create the producer now. In this case, we assign it to a variable called producer, but we can use the new method for a Kafka producer and provide the fact that we want to use the myProperties for the properties themselves. Now, as far as additional configurations are concerned, let me just talk about a few in general. Most of these we're going to talk about in more detail later on, but I just want to give you an idea of some other ones that you might consider, at least the most important ones, I think, overall. One is going to be ACKS, or abbreviation for acknowledgement. This is actually going to be a way to determine whether or not the message the producer sent to the Kafka broker successfully reached the Kafka broker and was stored in the partition that was supposed to go, or partitions if we're using replication. So there'll be a section on that in more detail later on. You assign a CKS to a numeric value that indicates really the number of configurations or a number of partitions that have to actually respond back with a successful completion of the value that's been passed in. Next thing we're going to look at is buffer.memory. Buffer.memory is associated with how much memory can be used by the producer to store information about records that are going to be sent to the broker. And now initially, it won't send a record every single time it receives it. It'll actually store these inside of a buffer memory and set them in batches essentially. And this is actually specifying how much memory we can allocate towards that. That's important, by the way, because we don't want to fill up memory really quickly. We want to make sure that if it gets to a certain memory size, they don't batch things up at that point and send them off. There's another option that's related to that called retries. This is a value that specifies that when a fail occurs, when we try to send the information to the broker, how many times we want to keep trying to send that over and over again. That does require us to handle the process of when error occurs, and we'll talk about how to deal with that a little bit later on as well. Another one that's kind of important to know about that we'll see in more detail is batch size. This is actually how many records that we want to collect before we send it to the broker. The producer can use buffer.memory to indicate how much memory size to use before we batch things off and send it, but what if it takes 30 minutes for us to get to the buffer memory maximum? We don't want to wait 30 minutes to send these messages off. The batch size indicates in bytes how big we want for a minimum size of the records before we send them off to the producer. Okay, in this lesson we're going to talk a little bit more constructing producers. And let's talk about some use case scenarios. So producers are very flexible, and how you actually create your producer functions should really be modeled upon the use case that you're trying to match. And there's several considerations that you want to take into account when you actually put together what type of producer functions you want to utilize. One thing that you want to think about is message loss or duplication permitted? And the reason why this is important is because it'll have to do with how we deal with failures when we try to send information to the broker. How do we deal with those failures? So there's several different techniques that we'll talk about in the next few slides here to handle that. We also want to consider latency and throughput as well. Those are some major considerations. And to take these considerations into account, we have to understand this next concept, which is the idea of batching. So the idea is that a producer is going to collect a bunch of data from multiple records before it sends it to a partition. There are two key configuration settings that you want to know about when it comes to batching. Actually, there's more than two, but two of them are key. The batch size, which I've mentioned in a previous lesson. So we'll batch things together into a collection of records that we want to send that to that partition, and we can specify in bytes how big this batch actually has to be before we send that information off to that partition. The other one that you should know about is called linger.ms. If we reach a batch size limit, it just sends off the batches and that's all there is to it. But what if it starts collecting things in this batch and then we never really get to that maximum size, or it takes a long time to actually get there? So maybe it takes 5 minutes, and that's too long for us. So we also have this thing called linger.ms. Linger.ms is going to be in milliseconds how long to wait until we definitely send off the batch, no matter if we reach the batch size limitation or not. If you set this to a value of 0, which it actually is by default, then the batch size has no purpose because it doesn't do any batching whatsoever. It just sends off information that it gets as it gets it. But if you set the batch size, then you may want to also send the linger.ms, so it doesn't sit there waiting until it reaches a certain size before it actually sends off the batch information. So if you do more batching, then you get a higher throughput, because what happens is when it takes that information, as we mentioned before, it compresses it into a byte array, so it'll actually go faster through the network to get to the destination. But we do have a higher latency as a result, so there's give and takes that you have to consider here. And think about your use case scenario as far as which is more important. Is it better for the data to be transported quicker across the network, or is it more important that actually the reports or the messages go through at a quicker rate than if the data itself is compressed or not? All right, so the last thing we have here is this thing called acknowledgement settings. So again, the idea is that once a record or message has been sent to a partition, that we need to determine whether or not that was successful, because if it was successful, then we know that we don't have to send the information again. But if it's not successful, we may consider resending the data again. So we have 3 different possible settings that we can set ACKS parameter to. This is when you set up your producer. It's one of the parameters you can set. Set it to a value of 0, 1, or the last one is either all or -1. They mean the same thing. The idea of 0 basically means let's send the information and we won't even care what the response is at all. Either it worked or didn't work. We're not going to really worry about it too much at all. We're just going to keep sending information to that broker from that point on. If it's set to a value of 0, there's no guarantee that the server or the broker has received the information or stored it or committed it or anything like that at all. We do get high throughput as a result, but we get really low latency. And the big problem with using the acknowledgement value of 0 is you could end up with message loss as a result. If you'd use acknowledgement value of 1, this is actually going to provide a medium throughput and medium latency, and message loss is going to be more rare, because what you're saying here is that we're going to ask the primary partition to respond back with, yes, I've got this data and I'm ready to commit it. What we won't do is ask for the primary partition to query all its replicas to say whether or not they got the message or not. So if you have replication and you're using acknowledgement value of 1, we know that the primary partition actually got the message and received it and stored it in its log, but we don't necessarily know whether or not the replicas do or not. We could still get message loss because something could happen to the primary partition. It might go down after it's acknowledged this response and before it got a chance to replicate it to the other servers or the other brokers that are replicating the data. So it's possible that you get message loss, but it's a lot more rare than acknowledgement level 0. If you use all or -1, you definitely have a low throughput and high latency, but message loss is extremely rare because with this one, not only does the primary partition, the leader, have to respond back and say, yes, I've received that message and I put it in my logs, but all of the replicas have to also respond back the same way. So we know the message has definitely been committed and that all the partitions are in sync. So we know that the data is definitely going to be there, not only in the primary partition, the leader, but also all the followers as well. Okay, in this next section, we're going to talk about really how the communication works with Kafka, and especially how to handle situations wherein the Kafka brokers don't acknowledge the receipt of a message, or how we're going to deal with that as far as are we going to try to resend or not try to resend, whatever the case may be. So there are 3 different methods to sending messages. We have simple send, synchronous send, and asynchronous send. Simple send is often referred to as fire and forget. We're basically going to say, send the message to the Kafka broker, send it to whatever partition it's supposed to go to, and I'm not even going to worry if it gets there or not. We're just going to assume that it does. We're not even going to use the acknowledgement setting that we talked about before. It just assumes that the value gets there, and we're not going to do any kind of check to see if it actually works successfully. So in that case, we'll get extremely high throughput, very low latency. We could lose messages as a result because we're not doing any kind of verification to make sure the message actually got there or not. Synchronous send is when we're going to send the messages using a method called send that we'll see, but we're also going to see whether or not any kind of result gets returned back again. And the way we're going to do that is by using a method called the get method. So the get method will actually return back whatever message were sent back from the Kafka broker. If there's no message that gets back, that means that the value actually got sent, or the record got sent to the Kafka broker. But if we got a kind of response back, we need to deal with that response. And then asynchronous send means we're going to call the send request, but we're not going to actually just see what kind of response we get back. We're going to have a function that we're going to create, kind of like a callback function, that will be triggered if any kind of message gets response back from the Kafka broker. And again, if the Kafka broker successfully were to put the information into its partitions, then there would be no message returned. But if any kind of error occurred, it would send back a message, and that would trigger, for an asynchronous send method, it would trigger a function to be called. So as far as the coding is concerned, here's an example of a simple send. So here we create the record itself that we want to send to the broker. So we've seen this before where we use the producer record to create a record, store it in this record, and then we're going to use a try function here. So we're still going to use a try function even though we're not looking at the return value coming back from the Kafka broker, because there could something be wrong in the producer.send method itself. So we'll still want to catch any kind of exception that might occur and do something with the exception. But we're not taking back any, or looking at any kind of exception that happens on the Kafka broker side. But we're going to send that record, and we're just going to blindly assume that it works. Another technique, again, is to use a synchronous send. This is very similar. We still create the record as before, but notice the add-on at the very end here, and that is to get back the information by using the get, and then that catch will actually look for any kind of exceptions from the get method that gets called back. And then asynchronous send looks a little bit different here. With an asynchronous send, we're going to create some kind of function that we want to use. So here's the my callback that we wanted to create, and it can do whatever you want to do. This is just some code we put in here just to demonstrate. But you can see when we do the call, we're going to do producer send, but we'll actually add in a function that my callback, we want to execute that if anything comes back from the Kafka broker. All right, so in this next section, we're going to talk about serializers in more detail. And let's start off with a review of what we already know about serializers. So remember that messages are going to be basically a collection of keys and values. And while Kafka makes use of byte arrays, the producer can use any kind of Java object for the keys and the values. So a serializer is basically a way of encoding the key and the value in a way that the producer and eventually the consumer will understand as well. We talked about the fact there's already some common serializers we can use. We talked about that in a previous lesson. There are 3 available by default, but we can create more. And in fact, that's what we're going to talk about right now. So you can create your own custom serializers. It may require some strong programming skills in whatever language you're working in, particularly maybe a Java, for example. Often it's not really necessary because there are other tools out there that provide the functionality of serialization. So for example, you can make use of Arvo, which we'll talk about in more detail in a few minutes here, JSON, Protobuf, and one called Thrift as well. So let's talk about Apache Arvo to begin with. So this was developed as part of the Hadoop project, and basically the idea is it serializes the data into a binary format to make the data more compact. It is language dependent, but it does have a lot of support in both Java and Python and some of the other primary languages as well. And one of the things it makes use of is something I'll talk about in more detail in just a few moments here, and that's called JSON schemas. So JSON schemas are really a way of defining what type of data you can actually have for your keys and your values. We can specify what kind of keys we can have, what kind of values we can have, and also for those keys and values, the format of them as well, whether we want them to be integers or strings or whatever they might be. So we'll talk more about JSON schemas in a few moments here. So the JSON schema can also be modified without impacting any existing data. It only impacts data in the future that gets sent when you serialize through Apache Arvo. Speaking of JSON, you can just use JSON straight up if you want to. It's a well-established serializer. It's been used for a long time now. Stands for Java Object Notation, by the way. You can also use a JSON schema in order to define what can be inside of the JSON keys and values. So you can see some of the code on that by looking at github.com. Look at the Confluence page for that. Google Protobuf is another type that you might be interested in. It actually is an abbreviation for protocol buffers. It's a Google project you can look into. It's language and platform neutral. And basically the idea is it defines a structure and generates the source code from that. So again, another link for you to find out more information about that on GitHub. Another one that's available to you is Apache Thrift. It is a cross-language serialization standard. It's got several different styles: binary, compact binary, HTTP friendly. GitHub actually has more information on a Kafka Thrift project. So now in order to be able to use either JSON or Arvo, you probably want to understand a little bit more about JSON schemas. So let's just go through a JSON schema and talk about different components that are available to them. The first thing you want to do is have this key value pair called namespace. Notice, by the way, the beginning curly brace for this JSON scheme, that's how you create an object in JSON. So an object is going to have key value pairs. We're going to have one called namespace. And the namespace is going to be part of a fully qualified name for this schema. So that's going to be important if we end up having 2 schemas with the same name. You'll see the name in just a few moments here as well. And then the type, if you're going to use Arvo, is going to be record. And then name is going to be whatever you want to call this. And again, if you've got 2 different schemas with the same name, the way that we end up with a uniquely qualified name is it uses a combination of the namespace and the name. And it does so in the opposite order. So you might be used to the terminology of like user.myorg.com, but in this case, it's actually com.myorg.user. But that creates a fully qualified name. And again, the advantage behind this is that if I do something like this and end up with 2 schemas named user, the namespaces should be different, and that will result in a different fully qualified name. So we'll be able to distinguish between the 2 when we actually store this in something called a JSON registry. But the key to this whole thing is really this last thing. This is actually what defines the different properties for the object that you're creating. So here's what we can actually put in that key or that value that's going to be an Arvo serialized key or value or a JSON serialized key or value. So let's just kind of step through this one at a time. You can see that the fields is actually a list of objects. So the square brackets around the curly brace objects creates a list. One really important thing when you create the list, make sure there's a comma between each element in the list. So after every set of curly braces is a comma before we have the next set of curly braces. And inside the curly braces, you're defining the different types of things you can put inside of this serialized data. So we can have a total of 4 different fields: ID, name, last, and phone. Those are the 4 things we can actually have. They're defined by the key value pair of name and then the value for that. And then you can specify what type of data you can put in that location. So for ID, we can have a type of integer. But if we don't use integer, it will break the JSON schema and that data won't be allowed. For name and last, the type is going to be string. For phone, the type could either be string or it could be null. So you can see how you can specify one or more types. For type, if the corresponding value is a single string, that means it's just one type. But if it's a list of things, a list of strings, it could be multiple types. And also the example for name shows you how you can have a default value. In this case right here, we have a default value of null, but you can use whatever you want for default value. So as far as the JSON schema location, that's going to be important as well. We need to specify where the JSON schema is. And one way you can go about doing this is you can include it in the message itself. I don't recommend that. That would definitely increase the size of the message. It might even double it overall. And it definitely is going to have an impact on your throughput when you're trying to send messages from the Kafka producer to the Kafka broker. Instead, you may want to use a JSON schema registry. The idea behind this is you put the schemas in a registry, and when necessary, when checking the values, it checks to see whether or not the registry matches up. So it's read by the producer when it serializes the data. And it's also read by the consumer when we deserialize the data. We haven't really talked about the deserialization process from the consumer, but we're going to see that in the upcoming lessons. So the identity of schema is also included in the message. So basically the name of the schema is in the message, but not the entire schema itself. And that's why you can actually look that information up pretty quickly in the schema registry. If you want to use this technique, there is a GitHub page. You can learn more about it and download that project and make use of it if you want to. So after this is all said and done, let's see an example now. So this is an example using Arvo serializer and a schema. You can see that we've added an option to our properties. So for our key serializer and a value serializer, we're going to use Kafka Arvo serializer. And then you can see that we're going to make use of a registry as well. So we have a schema.registry.url, and then we'd actually put in the actual URL. It says schema URL right now, but it would be whatever the URL is to get to that particular schema. Okay, let's get a little more detail in this next section on partitions. So let's first do a review on the partition information that we already know. Remember that if there's only one Kafka broker, then partitions really don't come into play at all. But if you have multiple brokers, you could configure the data that's being sent to the topic to be placed on or replicated on several different brokers. It really depends upon how you create the topic. Remember, there are a couple options that allow you to specify how many partitions that you want to use of all the brokers that are available and how many replication you want to have as well. That's something that can be added on to later on. We'll talk about topic administration in lesson 9. We'll talk about how you can add more partitions if you want. You can't remove partitions, but you can add more so you can scale out to a wider scale if you need to. Each instance of the data, again, is called a partition. The information gets stored in a log file, but we refer to the actual devices we're writing to as partitions. And a consumer can read from messages from any partition. Each consumer is also going to keep track of what message is read by using a numeric value representing something called the offset. So to give it a visual example how this works, let's take a look at the next demonstration here. So we've got two Kafka brokers, and those brokers are receiving messages. So there's two different partitions, and it's storing that information for this topic called topic A. So as messages come in, they'll actually be placed on the corresponding partitions and in the log files for those partitions. Each consumer can be configured to read from a partition. So in this case, we have two consumers, so it makes sense that each one's going to read from one of the partitions. So this consumer is going to read from the partition on the left-hand side of the diagram. The other one's going to read on the right-hand side of the diagram. In this case, by the way, you notice the consumer is a little bit behind. The offset for the left-hand consumer is 2, so it still has 2 more messages it needs to read and parse. And the right-hand consumer is on message number 3 for its messages. And I can't highlight this enough. Remember that even though it says topic A on both sides and 1, 2, 3, 4, those are 4 different messages for each partition. So a total of 8 messages here in this example. So the question that might come into mind is when a Kafka producer sends information to the broker, which partitions it actually go to. And this could be something that you define when you create your producer, because inside of the producer record, there is a way of specifying what I want to place or where I want to place the information. And that is the key, which in this case right here is customer phone. Now, I'm not saying that there's actually a partition called customer phone, but what happens is if you realize that you want to be able to store all the records in one partition for this particular situation, this particular rights I'm dealing with, and that way the consumer, when it reads from that one partition, it knows the data it's actually getting, you can actually provide a key, and the key is going to be used to determine which partition is written to. Again, it doesn't actually give an ID or a value of consumer phone, but what it does is it creates a hash map, and it maps the keys to partitions. And that way you know that all the things that you're sending to customer phone will go on the same partition. And again, that might make it easier for you to retrieve the information and do something with it on the consumer side. What if you don't use a key though? So the key is optional. You don't have to use it. You can just give your data, which is the typical key value pairs that you're using to store information. So here I've got a key called Sarah, a value called phone number of 1-555-5555. If no key is provided, then Kafka is going to pick a partition to write to. Now, there are ways you can actually modify how the writing works and specify where you want the partitions to go, but we'll talk more about that later. Right now, just realize that if you don't specify how you want to balance out the partition rights, it uses a round-robin approach by default. Hello and welcome to Lesson 8, Writing Consumers. In this lesson, we will dive into the concepts and code for creating consumers, the component of Kafka that reads the messages. We'll start with key concepts of consumers, including consumer groups. We will then discuss how to create a consumer and subscribe to topics. In this lesson, we will also cover the concepts of polling, commits, rebalancing listeners, and deserializers. Okay, now let's get a little more into understanding how consumers work. So lesson 8 is going to focus on writing the consumers. And we're going to focus on the theory of what consumers are and consumer groups and some other factors as well. So let's start off with understanding consumers to begin with. So we've seen this diagram before where we have producers sending messages to the Kafka cluster. We're sending it to a specific topic, and that information is going to go to individual partitions. And then the consumer is going to read the information by performing something called a poll operation, and that'll retrieve data from those particular partitions. If we have multiple consumers, they're all doing polls on topic A, they're independent of one another, so they'll all get a copy of all the messages as a result. But we could take these consumers and place them inside of a consumer group. If they happen to be inside of a consumer group, now they're going to actually work together. So in this case, you can see that we have 3 consumers. That means each one can retrieve information from one or more partitions for that specific topic. So here we have a consumer group that we're reading from 3 partitions in topic A. Each one of these is actually polling a different partition. So each one's going to have a different offset based upon how many messages are in that partition. Typically, partitions get sent messages round robin, but as we discussed in a previous lesson, there is a way of actually specifying exactly what partition you want a message to go to when you're acting as a producer. So it's possible that one partition may have a lot more message than another partition. So in this case right here, you can see that the first consumer has an offset value of 3 because it's up to date and it's read all the messages from the first partition of topic A. The second consumer has an offset of 1. It's also up to date and it's reading from partition 1 from topic A. And the third consumer has an offset of 2 because it's pulling from the third partition of topic A. As new messages come in this case we have 3 more messages that appear for this particular partition 1. You can see those 3 messages get consumed by the middle consumer, and as a result, the offset for that consumer gets updated to a value of 4. Okay, in the last lesson we kind of introduced consumer groups, but there's more details about consumer groups that we need to discuss. So in this section we're going to talk about consumer groups in more detail. There is a situation where you might just have one consumer inside of a consumer group. If that's the case, it's going to pull all the partitions, so all the data is going to go through that one consumer. It'll keep track of the offsets for each of the partitions it's pulling from. But if we had a situation where we had multiple consumers, now we have 3 consumers and 3 partitions, then each one of those can actually pull from a separate partition. So each one's going to have a separate offset based upon what it's read from those partitions. If we add a new partition to the topic, and that's something we're going to discuss how to do in lesson number 9, that means now we need to start reading information for that new topic. So what's going to happen is that new topic will be added, Zookeeper will be told about that new topic, and the next time a polling event takes place, the consumer group will be told, hey, there's this new topic you need to start reading from. So we'll talk about how in a few moments the consumer figures out now which of those 3 consumers is actually going to start pulling from that. But let's just say it's the last one here. It'll start pulling from there and reading information as a result. In this case, it might make sense to add another consumer. So if we add another consumer, now it's going to pull and it's going to keep track for that new partition that we have. It'll keep track of all the messages from this point on. So a few considerations when you create consumer groups. There are some advantages of having multiple consumer groups. One advantage is that a single consumer can easily be overwhelmed. There could be a lot of data coming through all those partitions. So by having multiple partitions, not only does it scale out and make it easier for you to have the Kafka brokers handle more data, but we can also have multiple consumers handle the data as well. So it allows us to scale out the data load on the consumer side too. There are some disadvantages of multiple consumer groups. Probably the most important disadvantage you should be aware of is the order of guarantee of the messages is going to be a little more complex, because you're going to have 3 or 4 or 5 separate applications that are reading the information, and that information is going to be in whatever order that it understands, but it's not going to be something that's going to be trivial to figure out the overall order of the messages. Now, there are date timestamps in the messages you can make use of if you want to, but keep in mind you're going to have to do a little extra work to make sure that the order is actually something that is easily to replicate and duplicate. We also could have problems if we have a partition rebalance. We'll talk about partition rebalance in the next slide in a second here. One really important thing to realize is there's really no advantage to having more consumers than partitions, except for the fact that maybe you might plan on adding more partitions in the future. So having a spare consumer makes it really easy, because as you add a new partition to the topic, you don't have to go through the process of adding a new consumer, although that's kind of a trivial thing to do, so it's not normally that big of an issue overall. So let's talk about partition rebalance, because this is an important thing to realize as far as how information is read by the consumer group. One thing to point out is that the first consumer that comes online acts as a leader. So it's the one that talks to Zookeeper and keeps track of what partitions are available, and it also will go through the process of assigning partitions to each new consumer that comes online. Our partition rebalance is when the assignments of the partitions to the consumers has to be changed. And this could happen for several different situations. It could happen when a new consumer is added. It can also happen when a consumer is removed or crashed. And a rebalance results in a very small window when consumers are not consuming data. It also could result in an issue where a consumer was reading from one partition and now it's reading from a different partition instead. And that could be a little bit of an issue as far as handling data is concerned, and we'll talk more about how to deal with that in another lesson. Okay, let's jump into some basic consumer configuration. It'll be very similar to the way that we configure producers. The first thing we need to do is create the property object. So in this case right here, we're going to create a myProps variable that will contain the outcome of the new method for the properties class. And then what we're going to do is start populating that. And if you think about this, it's just like how we did this when we created the producer. We need to specify where the Kafka brokers are. So we're going to have a key called bootstrap.servers, and then we're going to have a value that's going to be one or more brokers, which will be the IP address or host name, followed by a colon, and then the port that the broker is listening on. Then we need to specify how we're going to deserialize the data. So the deserialization must be matching up with whatever the broker serialization method was. We'll have a section a little bit later on talk more about deserialization in another lesson. But in this case right here, we're just going to deserialize the key and the value as if they were string serialized. And then something a little bit different that you're not used to seeing when you create producers is we need to specify what group we're going to belong to. So we need to have a property called group ID, and this is how we can determine whether or not this particular consumer is going to be part of a group or which group it's going to be part of. In this case, it's going to be part of a group called my group. Even if you only have one consumer in a group, you still have to have a group ID, so make sure you specify that parameter. And the last thing we need to do is define the actual consumer itself. So passing in the values of the properties that we've created up till now will create the consumer. Okay, now we know the basics of creating a consumer. Let's talk about how we can subscribe to the topics. So in order to do this, we're going to use the subscribe method. We need to specify which topic or topics the consumer will read. And again, the way we're going to do this is going to use a consumer.subscribe method. So here's an example of consumer.subscribe. We can specify the topics we want to read from. Now I know you might think, well, don't we just read from one topic? Well, a consumer can read from multiple topics. If you want to read from multiple topics, you can use the array add list and then specify the list of topics that you want to read from. You have some flexibility as far as how you're going to specify the topics. It can either be a single string or multiple strings or even a regular expression if you want to. So in this case right here, we're going to have a single string. We're going to read from a topic called topic 1. In the second example, we'll read from two topics, topic 1 and topic 2. And the third example, we're going to read from anything that begins with name or address. Now, if you're not familiar with regular expressions, you may want to just look into them a little bit because they are a very powerful way of expressing a pattern that you want to match, but they're not necessarily a really simple thing to utilize. The example we have on the screen right now actually is fairly simple. If you look at the example, we have name followed by a dot or a period and then an asterisk character or star. So the dot star represents 0 or more of any characters at all. So this could match name ABC, name XYZ. It could just match name all by itself as well. But it does have to start off with a value of name for the match to occur. And the same thing for address dot star. We're trying to match anything that begins with address and has any characters after that at all. Regular expressions, like I said, are really powerful tools, so you can use them to put together really complex patterns of things that you want to match. In a situation where you have a lot of topics that you want to potentially match, regular expressions could be a really powerful way of going about doing that. Keep in mind, though, that most likely you'll be able to decide how the topics are named. So if you put together a good naming convention, it'll make it a lot easier for you to match the different patterns when you use the regular expressions. Last thing to point out here is you have to list all the topics each time you call subscribe. So let's say at some point in time that you decide that you want to subscribe to other topics. It's not an incremental process. So for instance, if you had done this to consumer subscribe, that's the middle example where we describe from topic 1 and topic 2. And then later on, you do the consumer subscribe in the last example, or subscribing for named dot star and address dot star. That means you would no longer be subscribing to topic 1 or topic 2 anymore. So you want to make sure you include all the topics each time you call the subscribe method. Also, partitions are assigned by the assign function. It's not something we'll get into too much in this class, but if you want to say this consumer is going to read from this specific partition, you could do that with the assign function. And again, that comes back to something we discussed earlier in the training videos where I mentioned that you could make it so that a producer writes messages to a very specific partition. And if you want to have a consumer read from that specific partition, you can use the assign function if you like. Okay, let's talk a little more in detail about what happens during the pull operation. So first of all, let's explain in more detail what the pull loop actually is. As we already know, consumers can fetch messages from multiple sources, and so a pull is really an event loop, so it's going to continuously occur over and over and over again. And the idea behind this is that several actions will take place each time a pull loop occurs. So during the pull loop, one of the things that could happen is partition assignment. So when a consumer first starts up, it'll do a pull loop. It'll ask the consumer leader, hey, what partition can I actually read from? And then the partition assignment will occur at that point in time. Another important thing that happens during the pull loop is message fetching. So that's when it actually fetches the message from the partition that's reading from. Another event that might occur during a pull loop is rebalancing. So this is important because if a consumer group has a rebalance occur, that means that this consumer may have to now read from a different partition. So it's an important thing to actually have that pull loop occur so the consumer knows about the new partition it needs to read from. And then the other kind of coordination events take place during this time as well. One important thing to point out here, each consumer has to run in a separate thread. I put here each consumer should run a separate thread. Probably should put each consumer must run in a separate thread. It's a rule. You could actually have multiple consumers that are a part of different consumer groups in the same thread, but two consumers that are in the same consumer group should not be in the same thread. So here's an example of some code that shows you how a pull loop occurs. So we'll use a try block in this case right here. It's going to do the while loop, and as long as true is true, which it always is, it'll go ahead and do that consumer.pull. You notice there's a value that's being passed in of 100. That means it's going to do a pull every 100 milliseconds. So that's an important thing to actually have that continuous polling occur. Certainly, as we've discussed before, you can have a lot of messages appearing inside the partitions in a very short period of time. So having the pull loop be a very small value makes sense. So though in some cases it may not, I'm going to talk about how to deal with situations where you really don't have a lot of messages that you need to pull on a regular basis. So we'll discuss how to do that in a moment here as well. By the way, the for loop here, all it does basically is print the information that's being retrieved to standard output so you can actually see the information on the screen if you're trying to use this as a demonstration. When the while loop were to exit, so obviously while true is always true, but you can stop the thread if you want to. If that happens, then we'll do the finally operation. And this is a crucial thing to do. We need to close the consumer because that will tell the leader of the consumer group that this consumer is no longer consuming anymore. Eventually, by the way, that would happen anyway, because remember that there's a heartbeat that takes place between each consumer and Zookeeper. And so if that heartbeat is lost, then Zookeeper tells the leader, hey, you no longer actually have that consumer running anymore. And so it'll cause a repartitioning of all the different consumer groups and start reading from different partitions as a result. But just keep in mind that that actually is something that's just kind of nice to actually do this on your own by using consumer.close. And that way there's no downtime of consumer messages being read. Now, there is an alternate to using short timeouts. So in some cases, it doesn't make sense to have a very short timeout. Remember, by the way, we have a very small heartbeat interval. It's normally 2 seconds, so having timeout be 100 milliseconds makes sense. But instead of doing that, you may want to use long.max value. Now, in this case, what's going to happen is it's going to wait until there's any messages to actually pull. The only drawback about this technique is that the finally operation may never occur if you have a max long value. So what you could do is make use of something called a wake exception. So wake exception would actually be when the thread is shutting down, it will trigger a consumer.wakeup function to execute. And we can have our wake exception here that would actually pop us out of the while loop and do the finally statement, which is going to be consumer.close. Okay, now we're going to jump into a very important topic as far as consumers are concerned, and this is the topic of commits. Now, before we jump into that, let's do a quick review of what we already know about the offset. Remember that each consumer keeps track of where it is in the partition by using this thing called the offset. So here's an example where you've got three partitions, partitions 0, 1, and 2, being read by three consumers, and as you can see, all of their offsets are up to date as far as the current messages that are in the partitions. If a few more messages pop up in partition number 1, that means that the consumer is going to consume those messages, and when it's all done, it's going to change its offset to a value of 4. So it's important to keep track of the offset because when the consumer reads from the partition again, it's got to know where to read from. It's got to send a message saying, hey, show me anything that's happened since partition entry number 4. The commit process is a little bit different than the offset. The offset is the current position that a consumer is in a partition. The commit has to do with how that offset information is updated within the brokers themselves. So within the Zookeeper environment, there's actually a topic that we actually write to. In fact, this topic is actually called __consumer_offsets topic. But the commit basically is a way for the location of where each individual consumer is currently at to be stored not just on the consumer side, but within the Kafka broker itself. Now, why was this be important? Because if there's any type of rebalance that's triggered as a result, any new consumer that takes over a partition has to know where it's going to start reading from. So it's got to know where the offset, the last position was from the previous consumer. So consumers need to actually figure that out so they can start reading from the right location. So let me give you a couple scenarios that really could come into play and might be a problem as far as this is concerned. Scenario number 1 is when the committed offset is smaller than last message process. Now this could be a really common thing that happens, and if you think about it logically, it can make a lot of sense. So let's say, for example, the second consumer that we have is reading from partition 1 in topic A, and it's actually read all the way through event number 4. It's processed that event, but it hasn't gone back and updated its commit position back on the Kafka brokers. So __consumer__offsets, it says that for partition number 1, the committed offset is still 2. So it hasn't really done that yet, and then something happens to that consumer. It crashes, it fails, it gets a network disconnect, something happens, so it can no longer talk anymore to the Zookeeper or read information from the Kafka brokers. Now what's going to happen is if a rebalance occurs, the new consumer is going to go look at __consumer_offsets and says, hey, the last thing that was read was message number 2. Oh, look, there's a message number 3 and number 4. So that new consumer is going to say, my offset's 2. And it'll read message number 3 and 4 as a result. And now we have duplicate messages that are read. Now, it's possible that might not be a big deal because remember, the original consumer, it read those messages 3 and 4. Maybe it crashed before it actually went through the process of taking that data and sending it on to the next step. But if it didn't do that, now we actually have duplicates in data, and that could be a really bad thing. Imagine, for example, these messages are maybe credit card transactions, for instance. Well, now we have duplicate credit card transactions, and that won't make that customer very happy overall. So that's one scenario that we can come up with, and I'll talk about, by the way, different committing techniques in a few minutes. So you'll see when this scenario might occur more often than not, and how we can actually use a different scenario that would mitigate this potential problem. But there is another problem that could occur. Scenario number 2, and that is that the committed offset is larger than the last message processed. So in this case right here, the consumer has started to read the information. In fact, actually, in this example right here, the consumer actually really has read all the way up to 4, entry number 4 in the topic. But for whatever reason, it didn't get a chance to parse that data and do anything with it or update its offset before it actually went on. And again, I'll show you how that could actually might happen in a few moments as well. So in this case right here, That ends up now, since the consumer responded back and said, hey, I actually have a committed offset of 4, I read up to 4, but it never did on the back end any of the operations for 3 or 4. So as a result, now when a new consumer comes in, it goes, oh, well, the offset is the value that's in __ consumer _ offsets is a value of 4. Therefore, I should go ahead and start reading from 4 on. And now as a result, we end up losing the messages 3 and 4 as well. So how do these different situations actually occur? Well, let's talk about different types of commit operations. So one technique we can use is we're going to have the process happen automatically. The consumer is going to perform the commit. And the way we're going to do that is we're going to set a value of enable.auto.commit equal to a value of true. So this is going to be a parameter that we're actually putting the consumer when we first create the consumer. That's, by the way, default, so you don't really have to set this, but you should be aware what it actually is. And also realize that it's going to do the commit every 5 seconds by default. That's a configurable option. You can change that by using auto.commit.interval.ms and setting that up as a properties value, and then specify in milliseconds how often you want the commit to be performed. By the way, it happens to occur during the polling event. So during the polling event, if 5 seconds have happened since the last time they did a commit, it'll do a new commit. Now, 5 seconds is a pretty long time if you think about it. So let's say we have a really active broker that has, hundreds or thousands of new events taking place on the partition every second or so. Let's say that our polling operation is like every 100 milliseconds. So we're pulling a lot of things into the consumer. We're pulling a lot of records, and we're updating our offset quite a bit, but we're not going to update the commit value until 5 seconds have gone by. So it's certainly possible that if the consumer were to crash at any point in time, that it has gone through a lot more records than the offset, the committed offset actually specifies. So as a result of that, the committed offset could be out of date, and we can have a lot of duplicate records being processed. That was the first scenario I talked about before, where you can have all these duplicate records that occurred. I mean, in this case, very likely we can have duplicate records occur. You could modify the auto-commit interval to a smaller value, but you can't limit the issue entirely. You can't eliminate the issue entirely. There's always going to be, in this particular situation, the potential that you're going to have some duplicate messages as a result. So instead of using this technique, what you might want to do instead is use what they call a synchronous commit. The idea is to manually call the commit process with commit sync. And what happened is it'll do the commit after it's done the pull operation. So after it does the pull, it processes all the data, and then you run commit sync. So you'd manually actually write that inside your code, inside your try while loop that we talked about in the last lesson. So the commit sync will wait for the broker to respond with the accepted new commit operation. So it'll say to the broker, hey, I've got this new commit value. Let me know when you've got that, where you stored that information before I continue on any further. It'll throw an exception if a commit fails as well. If the commit fails, it'll retry automatically after the failure. By the way, you set enable auto commit equal to false when you use this technique. But the problem with this technique right here is that since it does wait for the broker to respond, there is a little bit of downtime. You've actually got a situation where you're blocked from reading any new operations or any new records for the poll method until you get a response back in. It may be a fairly quick response, but there is a little bit of downtime, and that could have an impact on actually reading the information. Your throughput is going to be a little slower as a result. Method number 3 is to use an asynchronous commit. So again, you're going to manually call a commit operation, but you're going to use commit async instead of commit sync. Normally you do this after you've done a polling event. So after all processing all the data, you can do a commit async. This one's different from the commit sync. It doesn't wait for the broker to respond with the accepted new commit. So it doesn't retry if any failure occurs. You could create a callback event in case any kind of error occurs. And you also have to set enable auto.commit equal to false. Now the drawback about this right here is since it doesn't wait for the broker to respond with any new commit offsets, there is a potential problem that you might continuously try to read new messages, update the value of the offset for this consumer, but the value is not being updated inside of the broker itself. And as a result of that, we now have a situation where if this particular consumer goes down, then we have an offset for this consumer that doesn't match the commit value inside of the record for the broker itself. Okay, so far we discussed the fact that we could have this process called rebalancing occur. Now we're going to talk about something called rebalancing listeners. So the idea is that if rebalancing occurs, we may have to have some operations performed by the consumers. For example, if a consumer has been assigned to a new partition, then any kind of things that it's been doing with the previous partition it was dealing with, it may have to actually finish those things up before it moves on to the new partition. So if a new partition is assigned to a new consumer, maybe we have to change the commit offset. We may have to process some events that deal with the data that we've been manipulating up until now, and like save data, close files, disconnect from databases, whatever operations need to take place before we can move on and start reading information from a different partition instead. So for this to work, what we want to do is first of all pass in a class called Consumer Rebalance Listener to the subscribe method. So that'll happen right off the bat. And then you have two different methods you can create within that class. You can create one called onPartitions_revoke. That will actually be called right before rebalancing occurs. So you can perform whatever actions you want to inside that method that you create. And then you can create also a method within the Consumer Rebalance Listener class called onPartitions_assigned. And that will actually have actions that take place after the rebalancing has finished. Let's finish up talking about consumers by discussing deserializers. And the good news is about deserializers is that once you understand serializers, which we discussed when we talked about writing producers, deserializers are pretty easy overall, I think. Really quick review of serializers. Remember, when messages are created, they're going to be a collection of key value pairs. So the producer is going to have to actually specify what kind of serialization we're going to use for these key value pairs. Even though Kafka makes use of the byte arrays, the producer can use any kind of Java object for the key value pair. The Kafka broker needs to know how to handle that data, of course. Serializers are code that package the data in a way that the producer and the consumer will understand as well. And we talked about the fact that there are some standard serialization techniques we can use, 3 of them by default, that are provided by the org.apache.comma.serialization.serializer interface. We also talked about the fact that there is a couple other ways we can use serialization. Arvo, for example, is one of the ones we talked about before, and here's an example where we actually made use of an Arvo serializer. And you're going to see that the way we're going to do this deserializer is going to be very similar to this technique. It's actually going to be pretty simple and straightforward, I think. So the deserializer is basically just to take the data from its serialized format and put it back the way it was before. So we have to know how the data was serialized. So you have to be aware of how the producer is going to serialize the data, what technique it uses. The same methods are available for the serializers. In addition to the common methods, we have Arvo, JSON, protobuf, and thrift, and any kind of customized serialization technique that you want to use, you could use as well. So an example of a common deserializer is on the screen right now. You can see that we're going to use the org.apache.kafka.common.serialization.string deserializer for both the key and the value. And we just have to specify those as parameters when we actually create the properties for the consumer that we're creating here. Here's an example of an Arvo deserializer, very similar to what you see when you do a serializer, except we're using Kafka Arvo deserializer instead of serializer. Hello and welcome to Lesson 9, Kafka Operations. There are several features of Kafka that can be used to modify the manner in which Kafka performs. This lesson will focus on these features and show you how you can modify them. We'll first discuss how to administer topics and then jump into a discussion on balancing and mirroring. We will also cover bandwidth and quotas. All right, so the first thing we're going to jump into in lesson number 9 is going to be topic administration. We've already seen a little bit about topic administration, but we'll see some more details in this lesson. So one thing we've already discussed is how to create a topic, but it's a good idea to review it to make sure it's clear. So we're going to use the Kafka-topics.sh script to create a topic. Use the -- create option. And for all the times that you're actually going to manipulate topics, you're going to have to use -- Zookeeper and then provide the host or IP address of the Zookeeper server, followed by a colon and the port number that Zookeeper is listening on. Then remember, when you create a topic, you have to specify a replication factor. A replication factor of an integer value 1 means there's no replication happening at all. But obviously, if you use a value 2, 3, 4, or whatever, you'll get replication on different partitions that are available inside of the Kafka cluster. And then use -- partitions and an integer value to specify how you want to spread the load across the different Kafka brokers that are available. And then lastly, use -- topic and then provide a string value of whatever you want to call the topic. We've also discussed how you can list basic topic information by using Kafka-topics.sh with the -- list option. And again, you just need to specify the -- Zookeeper option along with the host and port number. That just provides you a list of the topics, but if you want to get details about a specific topic, you can use the -- describe option. We haven't seen this one before, but it's a cool little option that will give you details about a topic. For instance, it'll tell you how many partitions there are in the topic. It'll tell you what the replication factor is for the topic. And it'll even tell you how many in-sync replicas there are. If you want to add a new partition to the topic, which is a really useful and important thing to be able to do because you may find that you need to add some more brokers in order to spread the load across more partitions. So to do this, we're going to use the -- alter option. You can also use this to alter other features as well, but this is just an example of altering partitions. You use -- partitions and then give a new integer value and then specify what topic you're modifying. One important thing to realize here is that you can add new partitions, but you can't delete any existing partitions. So if you have 5 partitions already, and you try to use -- partitions and you give a lower number than 5 for your integer value, you'll get an error message back as a result. So you can add more, but you can't delete any. However, you can delete the entire topic itself. So to do this, you can use the -- delete option, and then the normal options of -- Zookeeper and -- topic. For this next lesson, we'll talk about balancing and mirroring. Now, before we get into how to configure balancing, we should probably discuss what balancing actually is. If you recall from previous lessons, we talked about the fact that for every topic, there could be multiple partitions that are being written to from the producers. One of those partitions is considered to be the leader. So the leader is the one that decides what messages from the different producers go to what partitions for that particular topic. That information is stored inside the Zookeeper, so Zookeeper understands which partition is the leader. Remember, Zookeeper also keeps track of all the active connections, so if the leader were to go down, it would stop sending heartbeat messages to the Zookeeper, and as a result of that, we need to have a new leader take that role on. So there's a process called leader re-election that occurs, and that's what balancing is all about. There are 2 different methods that we can use for this. One's the automatic method, and for this one, what you need to do is in your server.properties file, set auto.leader.rebalance.enable equal to a value true. By the way, if you look in the file right now, you should probably find that that's what it's set to by default. So if you want to use the automatic method, there really is nothing for you to do. It's done that way automatically. But you can also use a manual method in which the process of electing a new leader is done manually by you. First of all, you need to set the auto.leader.rebalance.enable to a value of false in server.properties. And then when you want to perform a re-election, what you want to do is run the Kafka-preferred-replicate-election.sh script. The second thing we want to talk about is mirroring. And this is the idea of replicating data between clusters. So information that's actually in one cluster for a topic can be placed on another cluster. And one of the reasons why you want to do this is to increase throughput, so you can have consumers read from either cluster. And also you can have some fault tolerance as well. So if one cluster goes down, we have other clusters that have the information that we need. The number of partitions can vary, so just because you have a topic in one cluster with 5 partitions doesn't mean you have to have 5 partitions in the other cluster. So it's very flexible as far as that's concerned. To do this for a single topic, what you could do is use this command called Kafka-mirror-maker.sh. And for this, you have to specify a -- consumer config option with the consumer properties and a -- producer config option with producer properties as well. If you look at the config directory inside of your Kafka installation, you'll see a consumer property and producer property file that you can actually read through and see what kind of changes you can make to that. But the important thing here is that when you do this, you have to use the -- whitelist and specify what topics that you want to include as part of this mirroring process is concerned. If you want all the topics, you can say -- whitelist and then have an asterisk with inside quotes. It's a wildcard character or a globbing-like character. If you want to specify all but some topics, you can still do -- whitelist with an asterisk as an option, and then make a blacklist of the topic or topics that you don't want to have mirrored. Okay, for the next lesson, we're going to talk about bandwidth and quotas. So let's just talk about some concerns with the bandwidth. Obviously, producers can create a huge volume of data, and so can consumers as well. The problem with that is that it may be too much data for the broker to handle, and so if the broker's resources become monopolized, we end up with a situation where it's just too much information, and we get something called a denial service. The broker will stop responding because it's just too much data that's being sent to it. By the way, one thing that's really important here is if you come across denial services like this, you probably want to go ahead and expand and have more brokers. So create more brokers, create more partitions, and that way, if you spread that across multiple machines and multiple threads, you may not have this denial service situation take place. But if you know the limitations of a particular broker, then you may want to put together some quotas to limit the bandwidth potential of monopolizing a particular broker. So one thing to point out here is you can have some default quotas. So for each of your brokers in the server.properties file that you create, you can specify a value in bytes of how much bandwidth a typical consumer and producer will be able to have. So for example, if you want to have a 10 megabyte per second limit, here's how you can actually do the default value for the producer. So set quota.producer.default equal to essentially 10 megabytes, but in byte size instead. And we can also do the same thing for quota.consumer.default as well. You can have different values for the producer and consumers, but it makes sense to have a very similar value overall because whatever the producer produces, the consumer is going to have to consume as well, and maybe at a very similar speed overall too. That would actually be a default quote for the entire broker, but what you could do is also create some custom quotas. So you can use a utility called Kafka-configs.sh to modify existing quotas. So here's an example of one. In this case right here, we need to specify the Zookeeper that we'll have associated with our cluster. We're going to use a -- alter option to specify that we want to modify something. And then in this case, we want to add a configuration. So we're going to change the producer byte rate to 2048 and the consumer byte rate to 2048. The entity types that you see where it says any type user and any type clients, a user is a very specific consumer. So when you say entity type users and then entity type name, it says user 1 there italics because you're supposed to replace that with the actual consumer that this rule applies to. If you want to apply it to an entire consumer group, not just one specific consumer, then you can use the entity type of clients, and then when you say entity name, replace client 1 with whatever the consumer group ID is. If you want to display quotas, you can also use the --describe option for the Kafka-configs.sh script. And then again, you can use the any type and either use users or clients to specify if you want to see a quota for a specific consumer or a consumer group, and then give the entity name that's associated with that consumer or consumer group. Hello and welcome to Lesson 10, Connectors. Kafka Connect is a new feature of Kafka that provides an easy way to pull in data from non-Kafka sources. This is a rather large topic, so the goal of this lesson is to provide a good overview of what connectors are. We'll discuss some of the basic configuration of Kafka Connect, transformations, and the Connect REST API interface. In this next lesson, we're going to talk about connectors. We'll start with an overview. I do want to give you a little forewarning. Connectors could be probably a separate video class all by itself. This is going to give you enough to get started in connectors, but there's definitely going to be more that you want to explore beyond what I talk about in these lessons. So let's start off talking about what the purpose of Kafka Connect is. It solves a problem that you might have streaming data to and from other non-Kafka systems. So typically it's used to stream entire databases into Kafka. It's also useful if you have some type of data coming from an application server that doesn't have a Kafka component or a Kafka producer built into it. Some of the features you should be aware of: it does make use of a common framework that will standardize how the integration occurs from other data systems with Kafka. It will handle things like deployment and management, for example. There's two different modes that you can utilize. Distributed will actually have multiple Kafka connectors designed to distribute the load across multiple systems, and then you can use standalone as well. There's two different ways of configuring and starting up a distributed versus a standalone Kafka Connect system. In addition, you should realize that it uses REST APIs for manipulating the interface, so it makes it a lot easier to perform operations, to manage the connectors, and submit information to the connectors as well. It also handles the process of offset management. In fact, there's two different ways of doing that. The standalone system, you'll see, it makes use of a offset file that stores information in, and the distributed version, it actually uses a topic to store offset information. So it provides that offset information that you expect a consumer to actually utilize. It's highly scalable. So not only can you distribute across multiple systems, but that makes it scalable. You can add more Kafka connectors in the distributed environment if you want to. And it also allows for streaming integration as well and batch integration. Let's discuss the basic configuration of Kafka connectors. First of all, there are two different executables that you could utilize. You can use connect-standalone.sh if you want to have a standalone Kafka Connect server, or you can use connect-distributed.sh if you want a distributed one. There's some arguments that you want to be aware of. There's the config file, which is going to be the properties that you are going to specify for your Connect server. You can use server.properties as a starting point to build or modify this, but you're going to have some additional connector properties that you're going to add in there as well. And that's what we're going to discuss throughout the next part of this lesson. Some of the common properties that you're going to use, whether or not you're using a standalone system or a distributed system, are going to include the bootstrap servers, the key converter, and the value converter as well. Those are things that are common whether you're creating a Kafka producer, Kafka consumer, or in this case, a Kafka Connect server as well. So for standalone systems, there's an important property that you want to be aware of, and that is offset.storage.file.filename. So this is going to be set to a file, and the file is going to be where it's going to store the offset for the topics it's reading. Just like with consumers, we have to have an offset, but the consumers store it internally in memory, but we need to put it into a file for the Kafka Connect standalone server. If you're going to put together a distributed Kafka Connect server or servers, then there's several things that you want to be aware of. First of all, you don't want to include an offset.storage.file.filename property because distributed servers do not put the offset in a file. Instead, the offset's stored in a topic, a Kafka topic. That kind of makes sense, by the way, if you think about it, because if you have a distributed Kafka Connect, it could be distributed across multiple systems, and they wouldn't have access to that file directly. So it's got to be stored somewhere else, and so we're going to have to create on our Kafka cluster, we're going to have to create a topic to store that information in. Also, there's some other information that it can't store inside of a file. Things like task statuses and configs and things like that, those will all be stored in topics as well. So some of the important properties that you want to include in the config file, you're going to have a group ID. The default group ID is connect-cluster, but you can choose a different ID if you want to instead. If you're going to have multiple of these Kafka Connects, obviously you probably want to have different group ID names as well. Also, the group ID name can't conflict with a consumer group ID, so make sure that you're not using the same ID as a consumer group. You're also going to have to specify 3 specific topics where it's going to store information for you. You're going to have a config.store.topic, so this will be assigned to a topic name. You'll also have an offset.store.topic and a status.store.topic. Now, a couple things to point out about these. If you don't specify them, it does give you default ones. So if you didn't give these parameters, the config.stores.topic would automatically default to a connect-configs topic, and it would create that for you automatically as well. The same with offset.stores.topic. If you didn't specify the specific topic that you want to store that in, it'll automatically put it inside of the connect-offsets topic and create that topic as well. And as you can imagine, the status.stores.topic, if you don't specify that parameter, it would put it inside of a topic called connect-status, and it would create the topic automatically. There's nothing really wrong with using the defaults, except for if you do that, you don't have any choice as far as how many partitions it uses and the replication factor. It has some built-in values that it uses, but it might be better to create those topics manually and then use the value of those topics inside these settings here as well. Okay, so as far as where you place these different configurations, for a standalone, you put in a configuration file and you pass it in as an argument to the standalone startup script. But if you're talking about a distributed environment, since it's not going to have access, all those distributed versions aren't going to have access to a specific file on a specific file system, you pass that information in through a JSON. Some other commonly used configurations include a name that's going to be a unique name for the connector. In addition to that, you're going to have something called task.max. That's a maximum number of tasks or operations that could be created for the connector. We also have a connector class. So this is going to be the Java connector class for this connector. Typically, you're going to probably use something like org.apache.kafka.connect.file stream sync connector. So you can look up some other connector types that are available. That's one of the most popular ones that you might utilize. We also have the key converter and the value converter that you're going to include as well. We're going to talk about another feature of connectors called transformations. So a little brief introduction to transformations before we start talking about what you can do with them. They're designed to modify data in transit. So during the process where the data gets pulled from whatever location it's going to come from, like a database or an application server, you transform the data before it actually goes to its final end result. One message is going to be transformed at a time, and even though it seems like it might take a while to do that, it's a fairly lightweight operation. You can also create a train of transformations. So you can have one transformation that performs one operation, and then you can pass that to another transformation that performs another operation. As far as where you place these transformations, they'll be put inside the connector configuration itself. I'll demonstrate how to do that in a few moments here. There are several different transformation types you can have. Some of the more common ones include an insert field transformation. So you're going to actually add in a new field, either using some static data or some kind of metadata that comes from another location. You can replace a field's value as well. We can also mask a field. This one's going to replace the valid value of the field with something like a 0 or an empty string, something that's going to be a null value. We can also extract data, so pull data out of the information. We can include a timestamp as well, so we can modify the topic or record based upon the original topic and timestamp and use a new timestamp. And we can also make use of regex expressions too to make modifications. Now each one of these are not really called using the names I have on the screen. There's really a fully qualified name that you want to use. So for example, the timestamp router is really going to be org.apache.kafka.connect.transforms.timestamp router. So you can go look at that class and see what it consists of and see what functions and features are available inside of that. So here's a simple example. We'll set transforms equal to TS router. If there's more than one transformer, we'd place them as a list inside of that value. And then you can see the transformation itself. So we're going to use transforms.tsrouter.type is going to set to org.apache.kafka.connect.transform timestamp router. And there is a format we can use there. So you can see the format is going to be topic set to timestamp, or topic dash timestamp, I should say. And then the format we want to use for the timestamp is going to be year, followed by month, followed by day. So the last topic for this introduction to connectors is going to be related to the REST API that's available for connectors. So you should realize that Kafka Connect can be accessed as a server. It'll listen on port number 8083 by default. And the communication that you use to connect to it is through a REST API. Now, if you're not familiar with REST, I suggest that you look into a little bit to see what it's all about. It's a very simple interaction between a client and server that doesn't require any specific programming that takes place or any specific common programming language. So by using the API, it's very easy just to send commands into the Kafka Connect server to perform operations. And the common type of operations you're going to do are going to be GET operations, which are designed to return information from the Kafka Connect service. Post, which will be to create something in the Kafka Connect. Put will be to update an existing value in Kafka Connect. And then delete is to delete or remove something from the Kafka Connect service. So let's talk about some basic operations that you might use. One example would be get with the /connectors. This will actually return a list of active connections. If you want to create a new connection, we can use post and then /connectors. It'll create a new connector for me. The request itself should actually include in the body a JSON object containing the string field and the object field for the connector properties. And then we can also delete a connector if we want to. In this case, you're going to pass in a parameter, which is going to be the name of the connector that you want to delete. Some common GET operations that you'll see. If you want to see some information about the configuration of a particular connector, you'll use GET /connector / the name of the connector /config. It'll return back the configuration parameters for that connector. If you want to see what the current status of the connector is, and there's different status it could actually be currently running, it could be paused, or it could be failed. So if you want to see that information, you use GET /connectors, the connector name, and then /status. And then if you want to see a specific task operation, what's going on as far as a task is concerned, you say connector / the task name /task. It'll get a list of all the tasks that are currently running on the connector. And then for a very specific task, you specify connector / the name of the connector /task. And that task ID will be one of the task values that you got back from the previous GET operation, and then /status. Some common put operations, so these are things that you'll use to update parameters inside of connectors. So if you use put /name /config, you can update a parameter for a specific connector. Just give the name of the connector in place of the curly braces around the name. You can also use this to pause a connector, so temporarily pause it, and then resume it again. And then if you want to completely bring it down and bring it back up again, you can use the restart operation here. You can also restart any type of task that may have failed at some point in time by using the restart operation for that as well. Hello and welcome to Lesson 11, Kafka Streams. This is a newer feature of Kafka that provides an easy way to modify data on the fly. This is also a rather large topic, so the goal of this lesson is to provide a good overview of streams. In addition to covering the basic concepts of streams, we will also discuss how streams might be implemented in a system that also uses Kafka Connect. We're going to jump into Kafka Streams now. I want to give you a little forewarning before I get into this topic. It is a fairly large topic by itself, and my intention is not to go through a complete discussion of Kafka Streams. It is a component of Kafka that some people choose to use, some people don't use it. I want to give you like an introduction to it, to pique your interest in it maybe, and if you want to learn more, I'll give you some resources that you can learn more about it. So the first thing we'll talk about is the Kafka Stream API. It is a newer feature. It's available in Kafka 0.10 and later. And the goal is really to create these real-time applications or containers that will transform input topics into some other kind of format. So you may be transformed into output topics, it may be transformed into databases or some type of external application or service of some sort. The way it transforms the input topics into that is it just manipulates the data. There's a bunch of different types of data manipulation operations you can do. And so you want to think of this as kind of like a data flow programming or event stream processing, or I like to think of it as Kafka plus computation. Some of the key components you should be aware of: it is a continuous flow of data. Data is normally referred to as records rather than messages when you're talking about Kafka streams. The records should be key value pairs. It has a very small latency. It's highly scalable, and it's got fault tolerance in it as well. And the process itself can be in 3 different formats. It could be stateless, which is basically just mapping and filtering operations. Stateful, which is going to be like aggregate operations or join operations. And then you can also have this process called windowing. Well, basically you can say, I want to do or keep track of information for a certain period of time. So you can window in periods of time if you want to as well. The other thing that's important to talk about is the fact that stream processing is not a separate application. So like we saw with Kafka Connect in the last lesson, that was a separate application that was running, but stream processing is actually embedded within an application itself. It's not going to be performed on a broker or on a separate application like Kafka Connect. The next thing we're going to talk about is going to be the concepts and architecture of Kafka Stream. And one of the things I like to talk about first is the difference between Connect versus Streams, because there seems to be a confusion out there as far as what Connect is and what Streams are and how they're a little bit different. So with Connect, you're going to have a separate process. Remember we saw in lesson number 10, we can have like standalone processes or distributed processes, but they're going to be a process that actually handles all the operations that Kafka Connect's going to do. You also use a REST-based API to communicate to the Kafka Connect, and it's designed really to move large data sets in and out of Kafka. Although it can do transformation, that's not its primary goal. It's really designed to actually take data that's not Kafka-based and put it into Kafka, or take data from Kafka and put it into some type of other format instead. Streams are different in several ways. First of all, it's not a separate process. It's embedded coded. So it's going to be code that's going to be put inside of some other type of application, like a Java program that you create. There's no additional communication that's required. The streams just do the processing based upon the rule sets. And it's designed to create new data output. That's the big functionality that's trying to do. That data output could go to another Kafka topic. It could also go to Kafka Connect. It can go to a database. There's like several different ways you can actually send that information on to the next step. Again, the complete details are really beyond the scope of these videos. I didn't intend to actually create an entire discussion on streams or Connect. Those are things that I think that might be useful for you, but there's a lot of organizations out there that don't use Connect and streams. I just want to give you a glimpse at what they are about. The official Kafka documentation has an excellent demo that you can run through and explore how you can use streams in more detail. The last thing I want to talk about is the fact that it's often used with Kafka Connect. Streams and Connect basically kind of go hand in hand in some cases. So like, for example, we might have some source data that's not Kafka based, maybe some database that we're grabbing all the information from, and we use Kafka Connect to actually pull that into a Kafka environment. And then we could use our streams to manipulate that data using the different tools that are available in Kafka Streams. And then the output might go to another Kafka Connect, which may send it off to some destination like a database server or some kind of application server when it's all said and done. You have now reached the end of this course. I hope you have enjoyed it and feel ready to start using Kafka. Thank you for taking the time to view this video training course.